Lie back now, and let your eyes rest on the ceiling above you. If the room were dark enough, and if the roof were made of glass, you would be looking straight up into the night sky. People have been doing this very same thing for as long as there have been people. Long before cities lit up the ground, long before anyone knew what a star really was, human beings would lie on their backs in the cool grass or on warm flat stones and look up into the dark. They saw the same moon you have seen. They saw the same scatter of bright points, the same slow drift of the heavens turning overhead as the earth rolled quietly beneath them. That sky has always been there, a calm presence, a vast and silent ceiling hung with light. It asked nothing of them. It asks nothing of you now. It is simply there, waiting to be noticed, or waiting to be ignored, patient either way. On a very clear night, far away from streetlights and house lights and the glow of towns, you can see a few thousand stars with your bare eyes, a few thousand points of light, some bright and some so faint they flicker at the edge of seeing. That number, a few thousand, feels like a lot when you try to count them. It feels like an enormous crowd, a great gathering of lights strewn across the dark. But a few thousand is just the beginning. It is just the front porch of what is really out there. Because almost every other point of light you can see, beyond that small number of nearby stars, is not a single star at all. It is a whole galaxy, a whole city of stars, so far away that its billions of suns blur together into one soft speck of glow. That faint smudge you might notice in the corner of your eye on a very dark night, a little patch of haze that disappears when you look at it directly, that is not a cloud. That is light that has traveled for millions of years, light that left its home when no human eyes existed to receive it, crossing an ocean of emptiness, to land softly on your eye. And it lands there as a whisper, a tiny brush of brightness, carrying within it the combined shine of more stars than you could count in a lifetime. So we can begin gently, right here, with a simple word, galaxy. It is a word you have heard before. You may have heard it in school, or in a film, or read it in a book. But what does it mean when you strip away everything complicated and just hold the idea in your mind, like a smooth stone in your palm? A galaxy is a gathering. It is a vast gathering of stars, yes, but also of gas and dust, all of it held together by the steady pull of gravity. Think of it as a great family of suns, bound to one another across distances so huge that the space between any two stars is mostly a deep and perfect silence. Our own sun, the star that gives us daylight and warmth and makes the grass grow, belongs to one such family. We live inside a galaxy. We live inside a great wheeling disk of stars and glowing clouds, and that galaxy is called the Milky Way. But we will come to our own galaxy soon enough. For now, just let the idea rest beside you. A galaxy is a gathering of stars, gas, and dust, held together by gravity. That is all you need to carry forward. You do not need to memorize it. You do not need to be tested on it. There is no exam at the end of this. You can simply let the words wash over you like warm water, and if some of them sink in and others drift away, that is perfectly fine. That is what this is for. When you look up at the night sky, you are not looking at a flat ceiling painted with dots. You are looking into depth. You are looking into a volume so deep that your mind, quite sensibly, has no way to hold it all at once. Some of those points of light are close, in the way stars can be called close. Some are unfathomably far, and beyond the ones you can see, beyond the reach of your bare eyes, there are countless more. Telescopes have shown us that the sky is not just a scattering of individual stars, it is a scattering of galaxies. Each one of those faint smudges, those little patches of milkier light, is a whole separate gathering, a whole other family of billions of suns, turning slowly in the dark. The universe, as far as we can tell, is made of these gatherings. Galaxies are the big building blocks, the great neighborhoods of the cosmos. Our neighborhood is one of many, and the others stretch away from us in every direction, farther than any human journey could ever reach, farther than we have any real words for. So just let yourself imagine it, not as a problem to solve, but as a picture to drift through. A dark ocean, not of water but of space, and scattered across it like luminous islands, galaxies. Some of them are shaped like gentle spirals, some are smooth and round like eggs, some are ragged and torn. They glow in the dark, not because they are on fire, but because they are full of stars. Trillions upon trillions of stars, each one a sun, many of them with worlds of their own, all of them pouring their light into the emptiness. And that light travels. It travels for years, for thousands of years, for millions of years, for billions of years. When you look at a galaxy that lies, say, 10 million light-years away, you are seeing light that began its journey 10 million years ago. You are not seeing the galaxy as it is right now. You are seeing it as it was. You are looking back in time, through a calm and silent tunnel of pure distance. That thought can feel very large, and it is. But it is not meant to alarm you. It is meant to settle around you like a soft blanket. You are not small in a frightening way. You are small in the way a single note is small inside a long, slow piece of music. The note belongs. It does not need to be loud to belong. You belong here, in this moment, listening to these words, under this sky. Let us sit with the night sky a little longer before we move on. Imagine a warm evening, somewhere far from the glow of towns. The air is still. The ground beneath you is solid and steady. Above you, the sky has deepened from blue to a deep inky indigo, and the first stars have begun to prick through. As your eyes adjust, more and more of them appear. The longer you look, the more you see. It is as if the sky is slowly opening, slowly revealing itself, but only for those who are patient. There is no hurry. The stars are not going anywhere in a rush. They wheel overhead at the pace of the Earth's own turning, which is so slow you cannot feel it. You could lie there for hours and the constellations would only have shifted a little. The whole scene is one of immense quiet, immense calm, immense steadiness. Now take one of those faint smudges, one of those little clouds that is not a cloud. Hold it in your attention. That smudge, that tiny brushstroke of light, is a galaxy. It is a gathering of maybe 100 billion stars, 100 billion suns. Each of those suns is a ball of glowing gas, like our own sun, pouring out light and heat into the space around it. Around many of those suns, planets may orbit as our Earth orbits our sun. Moons may orbit those planets. Comets may swing through those distant systems on long, slow paths. All of that, a whole universe in miniature, a whole vast arrangement of worlds and lights and motions, is packed into that one faint smudge in your night sky. And that is just one. There are many such smudges. In a truly dark sky, you might see a handful with your bare eyes. With a telescope, you can see thousands. With a very powerful telescope, you can see millions, stretching away in every direction, like grains of sand on an infinite beach. Each grain is a galaxy. Each galaxy holds billions of stars. The numbers climb and climb, and the mind, quite wisely, lets them go. You do not need to grip the numbers. You can just let the feeling of them wash over you, the feeling of deep, deep space, the feeling of deep, deep time, the feeling of being held inside something so large that it has no edge, no boundary, no end that we can find. And here is a reassuring thought. All of it, every galaxy, every star, every planet, every drifting cloud of gas, is governed by the same quiet laws. The same gravity that keeps your feet on the floor, keeps the stars in their slow orbits. The same light that fills your room in the morning is the same light that left a distant galaxy millions of years ago. You are not separate from any of this. You are made of the same stuff. The atoms in your body, the carbon and the oxygen and the iron, were forged inside stars that lived and died long before our sun was born. You are literally made of stardust, a phrase that can sound like poetry, but happens to be a plain fact. The elements that make up your bones and your blood and your breath were cooked in the furnaces of ancient suns and scattered across space when those suns ended their lives. Gravity gathered those scattered elements together, slowly, patiently, over immense stretches of time, and eventually formed our sun and our earth and you. So when you look up at the night sky, you are not looking at something separate from yourself. You are looking at your own distant origins. You are looking at a family portrait painted in light. Take a slow breath in, and as you breathe out, let that thought settle. You belong to a galaxy. You belong to a universe. This whole journey we are about to take together, through the shapes and lives of galaxies, is really just a way of getting to know your own home on the grandest scale. And the journey will be slow and gentle. We will not rush. We will take each idea and turn it over quietly, like a leaf in the hand, looking at it from different angles, letting its shape become familiar. There is no destination we are trying to reach. There is no climax we are building toward. This is just a walk, a slow walk through the dark, with the stars overhead and the ground firm beneath us. You can close your eyes if you like. The images will still be there, behind your eyelids, inside the quiet theater of your mind. A galaxy, then. A gathering of stars, gas, and dust, held together by gravity. It is a simple idea, and a vast one. In the sections that follow, we will step slowly into our own galaxy, the Milky Way, and get to know its shape and its size, and the quiet place where our sun sits inside it. We will learn the language of light years, a way of measuring distance that sounds like time but is really just a way of making the immense numbers a little easier to carry. We will visit other kinds of galaxies, some that are smooth and round, some that are ragged and torn, some that are so small and faint they are only now being found by patient observers. We will look at how galaxies are born, how they grow, how they drift together and sometimes merge over billions of years. We will meet the quiet giant that sits at the center of our own galaxy, a black hole that holds the whole vast wheel together with its gravity, and we will approach that mystery without fear, just with calm curiosity. And we will end by drifting out to the largest scales we know, where galaxies themselves gather into clusters and long threads, forming a web that spans the entire observable universe. That is the path ahead, but you do not need to walk it all at once. You do not even need to remember where we are going. You just need to be here, now, in this moment, with the soft image of a dark sky and a scatter of faint smudges, each one a galaxy, each one a gathering of billions of suns, each one turning slowly in the quiet dark. So lie still, let your breathing slow. The night sky is above you, even if you cannot see it. It is always above you, whether it is hidden by clouds or washed out by city lights or simply on the other side of the earth. The galaxies are there, going about their slow business, just as they have been for billions of years. And you are here, safe and warm, drifting on the edge of sleep, held by gravity to a small blue world that circles an ordinary star in the outer parts of a spiral galaxy. That is where we will begin next, our own home galaxy, the Milky Way. But for now, just rest with the wide view, just rest with the quiet. The journey continues in its own time, and you are in no hurry at all. The journey continues in its own time, and now that time has come to turn our gaze a little closer to home. We have been drifting out in the wide view, looking at the night sky as a scatter of distant galaxies, each one a gathering of billions of suns. That view is true, and we will return to it many times. But now let us pull our attention inward, toward the one galaxy we know from the inside. The one galaxy whose stars we can see up close, whose shape we can feel around us, even if we cannot step outside it to look. This is our home galaxy. This is the Milky Way. The Milky Way is the galaxy that holds our sun. It holds our Earth. It holds every star you have ever seen in the night sky with your bare eyes. Every single one of those bright points, the bright ones and the faint ones, the white ones and the slightly blue ones, the ones that twinkle low on the horizon and the ones that shine steady overhead, all of them belong to the Milky Way. They are all members of the same great family of stars, the same vast gathering, held together by the same quiet pull of gravity that keeps our own planet circling our own sun. When you look up on a clear night and see the stars spread across the dark, you are looking at the inside of our galaxy. You are looking at our home from the inside out. The name itself, Milky Way, is a very old name. It comes from the way our galaxy looks to us from the ground. On a truly dark night, far from any city lights, you can see a pale band of light stretching across the sky from one horizon to the other. It is soft and hazy, like a river of thin milk spilled across the black. Ancient people saw this band and gave it names that spoke of milk, or of a road, or of a heavenly river. The Greeks called it the Galaxies, which means milky, and that is where our word galaxy comes from. The whole idea of a galaxy, the whole category of these vast gatherings of stars, is named after the milky band we see in our own night sky. It is a name that goes back thousands of years, back to a time when no one knew what it really was, only that it was beautiful and strange and worth giving a name to. What we now know, after centuries of patient looking and measuring and thinking, is that this milky band is the light of countless stars, not hundreds, not thousands, but billions upon billions of stars, so far away and so closely packed from our point of view that their light blends together into a soft, continuous glow. Imagine standing in a forest so large that the trees in every direction blend into a solid wall of green. You cannot pick out each individual tree because there are simply too many of them, one behind the other, stretching away for miles. That is what the band of the Milky Way is like. It is the blended light of stars so numerous that your eye cannot separate them. Each tiny fleck of light inside that pale band is a sun. Many of them are larger than our sun. Many are smaller. Some are older, some are younger. But they all shine, and their light all travels across the vast spaces of our galaxy to reach us, to land on our eyes as a single soft glow. So how many stars are there, all together, in this great gathering we call the Milky Way? The honest answer is that we do not know the exact number. It is far too many to count one by one, and many of the stars are hidden behind clouds of dark dust that block their light. But astronomers, the people who study the sky, have found ways to make careful estimates. They measure the total mass of the galaxy, they count the stars in small sample patches, and they build a picture from those pieces. The number they come to is somewhere between 100 billion and 400 billion stars. Let those numbers sit with you for a moment. 100 billion is a 1 followed by 11 zeros. 400 billion is 4 times that. Even the lower number is more stars than there are grains of sand on a large beach. Even the lower number is so large that your mind, quite reasonably, cannot hold it as a picture. It can only hold it as an idea, a feeling of vastness. And our sun, the star that gives us light and warmth and makes every day on Earth possible, is just one of those stars. Just one. It is not the biggest, it is not the brightest, it is not at the center. It is a perfectly ordinary star, of a very common type, sitting in a quiet part of the galaxy, doing what stars do. There are billions of stars very much like it, scattered across the Milky Way. Some of them surely have planets of their own. Some of those planets may be rocky and warm, like ours. Some may be cold and gas-shrouded, like Jupiter or Saturn. The galaxy is full of possibilities, full of other worlds, other suns, other arrangements of rock and ice and atmosphere. And our whole solar system, from the sun to the outermost comets that orbit it in a slow and distant circle, is just one tiny neighborhood in this much larger city of stars. It can help to think of the Milky Way as a city, a great, sprawling city of stars, with a dense downtown at the center and quieter suburbs spreading out around it. Our sun lives in the suburbs. Not the farthest suburbs, not the edge of town, but a comfortable distance out, in a region where the streets are a little quieter and the stars are a little more spread apart. If you lived in the dense center of the galaxy, the night sky would be very different. It would be brilliant with nearby stars, some of them so bright you might be able to see them even during the day. The constellations would be thick and tangled, and the dark would never be quite as dark. But out here, in our quiet suburb, the night is deep and the stars are fewer. We can see past our own galaxy's lights to the darkness beyond. We can see other galaxies, faint and distant, because our local sky is not crowded with too many close suns. Our position in the galaxy is a gift. It gives us a clear view outward, even as it gives us the Milky Band overhead, to remind us of where we live. Let us take a moment to picture the sun's place more clearly. The Milky Way, as we will explore in more detail soon, is shaped like a flat disk with a bulge in the middle. It has curling arms of stars and gas that wind outward from the center, like a pinwheel. Our sun is located in one of those arms, a smaller arm called the Orion Spur. It sits about 27,000 light-years from the galactic center. That is a number we will come to understand better when we talk about light-years. But for now, just hold it as a measure of great distance. The center of the galaxy is far, far away from us. The light from the center takes 27,000 years to reach our eyes. That means when we look toward the center, we are seeing it as it was 27,000 years ago, long before any human city existed, long before written history began. We are looking back in time, across a gulf of space that is also a gulf of years. The center of the galaxy, that dense downtown of stars, is a place of mystery that we will visit later in this journey. For now, just know that it is there, a bright and crowded region that we cannot see directly with our eyes, because too much dark dust lies between it and us. But telescopes that see in other kinds of light that can pass through dust, have shown us what lies there. A great swarm of stars, orbiting a quiet giant that we will meet in a later section. A black hole, a supermassive black hole, sitting at the very heart of our galaxy, holding the whole great wheel together with its gravity. But that is a story for another section. For now, we are just getting to know the Milky Way as a whole, as our home, as the great gathering that contains our sun and our earth and every star we can see with our own eyes. The stars you see in the night sky are all part of this one galaxy. The bright ones, like Sirius and Vega and Betelgeuse, are our close neighbors in the galactic suburbs. They are the bright lights of nearby streets in our cosmic city. The faint ones, the ones you have to look at sideways to see, are the distant street lamps, farther out in the same city. And then there are the very faint smudges, the ones we talked about in the first section. Those are not stars of the Milky Way at all. Those are other cities entirely, other galaxies, far beyond the borders of our own. When you look at one of those faint smudges, you are looking out of our galaxy entirely, past its farthest stars, into the deep space between galaxies, and all the way to another gathering of billions of suns. That is a humbling thought, but a calm one. It is a thought that places us, gently, in our true position. We are inside a galaxy, looking out. We are residents of the Milky Way, gazing through our own starry streets, toward the lights of distant towns. And yet, for most of human history, no one knew this. For thousands of years, people looked at the Milky Band across the sky and did not know it was made of stars. They looked at the faint smudges and thought they were just clouds, or perhaps small patches of glowing gas within our own system. It was only within the last few hundred years, a blink of time compared to the age of the galaxy itself, that telescopes became sharp enough to resolve the Milky Band into individual stars. And it was only within the last century that astronomers confirmed that the faint smudges were other galaxies, outside and far beyond our own. The story of our understanding is a story of slow, patient looking. No sudden leaps, no dramatic reveals, just generations of careful observers, building better tools, asking better questions, and gradually, gently, expanding the picture of where we are. Now, as you lie here in the dark, you can hold that picture in your mind. You are on a planet. The planet circles a star. The star is one of perhaps 200 billion stars in a galaxy. The galaxy is a great spinning disk of light and matter, 100,000 light-years across. And that galaxy is just one of countless others scattered across an ocean of space so deep we have no real way to measure it except with the slow crawl of light itself. This is the home address we have, written in full. Earth, Solar System, Orion Spur, Milky Way Galaxy, Local Group, Universe. It is a long address, but a calm one. Every line of it is held by gravity, steady and quiet, turning in the dark. Let your breathing slow as you sit with this image of our home galaxy, the Milky Way. Its name is soft on the tongue. Its presence is vast and gentle around us. It is not something far away. We are inside it. We are made of its stuff, the iron in your blood, the calcium in your bones, the oxygen in your lungs. All of it was forged in stars that lived and died in this very galaxy, billions of years before the Earth was born. When you look up at the Milky Way band on a dark night, you are seeing the light of your own origins. You are seeing the glow of the great stellar nursery that, over immense stretches of time, produced the elements that make up your body and your world. You are not a stranger to this galaxy. You are a child of it, returning your gaze to the bright places from which you came. So let that be our anchor as we move forward into the deeper parts of this journey. The Milky Way is home. It is the ground floor of our cosmic address. Every step we take from here, every new scale we explore, will build outward from this place. We will learn its shape in more detail. We will learn how it moves, how it holds itself together, how it compares to other galaxies we can see. But for now, just rest with this first glimpse. Our sun, an ordinary star. Our galaxy, a gathering of hundreds of billions of suns. Our place, a quiet arm of that great spiral, far from the bright and busy center, looking out into the deeper dark. The journey will take us further soon, but there is no rush. The galaxy has been here for more than 10 billion years. It will still be here, turning slowly, when you wake. You can let go of the details and just feel the shape of it, the vast, quiet wheel of light that carries us all. The next step, when it comes, will be a gentle one. We will begin to trace the outline of that wheel, to see the Milky Way's shape from the inside out, and to understand what kind of galaxy we call home. Now we can begin to trace the outline of that wheel, to see the Milky Way's shape from the inside out, and to understand what kind of galaxy we call home. This is not an easy thing to picture, because we are inside it. Imagine standing in the middle of a great forest and trying to draw a map of the whole woods. You can see the trees near you. You can see their trunks and their branches and the way they spread their leaves, but you cannot see the shape of the forest from above. You cannot see where the trees thin out at the edges, or where the clearings open, or how the land rolls beneath them. You have to piece it together from clues, from careful measurements, from the patient work of walking through the woods and noting what you find. That is what astronomers have done with the Milky Way. They have mapped a forest of stars from the inside, and the picture they have built is beautiful and calm and worth holding in the mind. The Milky Way is a spiral galaxy. That much we can say with good confidence, but it is not just any spiral. It is a particular kind, called a barred spiral. The word barred here does not mean blocked or closed off. It means that across its middle, running through its center, there is a long bar of stars. Think of a pinwheel, the kind a child might hold in their hand and blow on to make it spin. Now imagine that at the very center of that pinwheel, instead of a small round hub, there is a straight bar, and the curling arms of the pinwheel attached to the ends of that bar. That is a barred spiral. Our galaxy has a central bar made of stars, a dense, elongated cluster of suns that stretches across the heart of the Milky Way like a luminous spine. From each end of this bar, the great spiral arms unwind, curling outward into the disk. This bar is not something we can see directly with our eyes. It is hidden from us by distance and by dark clouds of dust that block visible light. But telescopes that see in other kinds of light, light that can pass through dust like a warm hand passes through water, have revealed the bar to us. Infrared light, radio waves, these invisible forms of light travel right through the dusty curtains and show us the shape of what lies behind them. And what lies behind them is a bar of stars, a long, bright structure that is perhaps 27,000 light-years from end to end. That is roughly the same distance as our Sun is from the galactic center. The bar is enormous, a central feature of our galaxy's architecture, and the spiral arms flow outward from its ends, like water curling away from a slowly turning paddle. The spiral arms themselves are the most famous feature of galaxies like ours. They are the curling lanes of light that give spiral galaxies their name and their beauty. In the Milky Way, there are several major arms, and our Sun lives in a smaller offshoot of one of them. The major arms have names. There is the Perseus arm, the Sagittarius arm, the Norma arm, and the Scutum Centaurus arm, among others. These names come from the constellations they pass through when we look up at them from the ground. The arm we live in is called the Orion Spur, sometimes called the Orion Arm or the Local Arm. It is not one of the grand main arms. It is a smaller branch, a quiet side road off the great highways of stars that wind around the center. Our Sun, and our whole solar system with it, sits inside this spur, about 27,000 light-years from the galactic center. That places us a little more than halfway out from the center to the edge of the disk. We are not in the crowded core, and we are not at the lonely fringe. We are in a comfortable middle distance, a quiet suburb in the grand city of the galaxy. The whole disk of the Milky Way, from one edge to the other, is roughly 100,000 light-years across. That number is hard to hold in the mind, and we will spend an entire section soon just sitting with what a light-year really means. But for now, just know that the disk is vast. If you could travel at the speed of light, which is the fastest speed anything can go, it would still take you 100,000 years to cross from one side of the galaxy to the other. 100,000 years is longer than human beings have had written language. It is longer than we have been building cities or planting crops. It is a span of time so long that entire ice ages have come and gone within it, and yet, for the galaxy itself, that crossing time is just a modest measure. The galaxy has been here for more than 10 billion years. 100,000 years is a mere heartbeat in the life of the Milky Way. The disk is not solid, of course. It is made of individual stars, each one moving in its own orbit around the center, like planets around a sun but on a much grander scale. The stars nearer the center take less time to complete one full orbit. The stars farther out, like our Sun, take longer. Our Sun, sitting about 27,000 light-years out, takes somewhere around 230 million years to make one full trip around the galactic center. That is a long time. The last time our Sun was in this same position, relative to the galaxy's center, dinosaurs were just beginning to walk the Earth. The time before that, the Earth itself was still young. This slow, stately dance is the rhythm of the galaxy. It is a rhythm so slow that no human lifetime can feel it. We can only infer it, measure it, and hold it in our minds as a quiet truth. The disk is also not flat like a perfect plate. It has some thickness to it. And if you could see the Milky Way from the side, it would look like a thin lens, thicker in the middle and tapering toward the edges. At its thickest point, in the central bulge, it might be a few thousand light-years from top to bottom. Out where we are, the disk is thinner, perhaps 1,000 light-years thick. But even 1,000 light-years is an enormous distance. It means that if you traveled straight up, perpendicular to the disk, at the speed of light, it would take you 1,000 years to emerge from the top of the galaxy's starry plane and look down on it from above. We are embedded deep within that plane, surrounded by stars in every direction along the flat disk, but with fewer stars above and below us. That is why the Milky Way band looks like a narrow stripe across the sky. We are looking along the plane of the disk, into the dense, crowded layer of stars, and seeing it edge on. The band is thin because the disk is thin, at least compared to its great width. Around the disk there is more. The Milky Way is not just a flat wheel of stars with nothing beyond it. It sits inside a much larger, fainter halo of old stars and globular clusters. Globular clusters are tight spherical swarms of very old stars, some of the oldest stars in the galaxy. They orbit the center in long, looping paths that take them high above and far below the plane of the disk. These clusters are like ancient relics, fossils from the early days of the galaxy's formation. There are about 150 known globular clusters in the Milky Way's halo, and they are a clue to how our galaxy grew, which is a story we will come to in a later section. For now, just picture the halo as a faint, diffuse cloud of old light surrounding the bright disk, a soft aura of stars that have been here almost since the beginning. And at the very center of it all, inside the bar, inside the bulge of older stars, there is a point of immense gravity, a supermassive black hole. We will visit this quiet giant in its own section because it deserves a slow and careful approach. But it is part of the shape of the Milky Way too, the anchor point around which everything else turns. Its gravity helps hold the bar in place, helps guide the orbits of the stars in the central bulge, and sits silently at the heart of our galaxy, exerting a pull that is felt across the entire disk. This, then, is the shape of our home, a barred spiral galaxy, about 100,000 light-years across, with a central bar of stars, several grand spiral arms curling outward from the bar's ends, and a smaller spur where our sun quietly resides. The whole disk is rotating, slowly and majestically, carrying its hundreds of billions of stars in a great circular flow. The sun, with its family of planets, has made this circuit many times since it was born, and it will make many more circuits in the billions of years to come. We are passengers on a vast carousel of stars, a wheel of light turning in the dark. It is worth pausing here, with this image, and letting it settle. A barred spiral galaxy, a bar of stars across the middle, curling arms of brighter light winding outward. A disk 100,000 light-years across. Our sun, in a quiet spur, 27,000 light-years from the center. These are the basic facts, and they are enough. You do not need to memorize the names of the arms. You do not need to remember the exact thickness of the disk. You can just hold the picture in your mind, like a soft, glowing map, and let yourself drift within it. Imagine, if you like, rising slowly above the plane of the galaxy, rising through the thin layer of stars, the disk growing thinner beneath you as you ascend. The stars that once surrounded you in every direction begin to fall away above and below, until you are looking down on a great pinwheel of light. The central bar glows warmly, a dense concentration of older, yellower stars. The spiral arms curl outward, traced by the blue-white light of younger, hotter stars, and the pink glow of gas clouds where new stars are being born. The spaces between the arms are not empty, but they are dimmer, quieter, filled with older stars that have drifted away from the bright lanes of their birth. And out on one of those arms, on a small side branch, a tiny, unremarkable yellow star shines steadily. Around that star, 8 planets trace their own small circles. On the third planet, warm and wet and blue, there are oceans and mountains and forests, and there are beings who look up at the night sky and wonder. That is us. That is home. Seen from above, the whole galaxy is a calm and luminous island in the dark, turning slowly, silently, holding us all. This picture of the Milky Way as a barred spiral is not just a guess or a dream. It is built from decades of careful work. Astronomers have measured the distances to thousands of stars. They have mapped the motions of gas clouds. They have observed other spiral galaxies and compared their shapes to ours. They have used radio telescopes to see through the dust that blocks our view of the center. Piece by piece, they have assembled the map. It is a map made from the inside, and it is still being refined. Some details remain uncertain. The exact number of spiral arms is still debated. Some studies suggest 4 major arms, others suggest 2 main arms with several smaller branches. The true shape of the bar is still being measured, but the broad picture is solid and well tested. We live in a barred spiral galaxy of roughly 100,000 light-years across, and our sun orbits the center at a distance of roughly 27,000 light-years. These are facts that have been checked and rechecked, measured and remeasured by many different teams using many different methods. They are as reliable as any facts we have about the distant universe. And yet, for all that careful work, there is something gentle about this knowledge. It does not demand anything of you. It does not require you to act or to change or to do anything at all. It is simply a description of where you are, on the grandest scale. It is a way of saying, this is your home, this is its shape, this is its size, this is your place within it. You can let that knowledge rest beside you as you drift towards sleep. You are here, on a small blue world, orbiting a quiet yellow star, in a spur of a spiral arm, in a barred spiral galaxy called the Milky Way. The galaxy turns, the stars shine, the dark holds it all in a soft and endless embrace, and that is enough. In the next part of our journey, we will take one of the numbers that has appeared several times now, the light year, and we will hold it up to the light and turn it over slowly until it feels less like an abstraction and more like a real measure of the spaces we are talking about. We will learn what a light year really means, not as a number but as a distance the mind can almost touch. For now, though, you can let the numbers blur. You can let the shape of the galaxy float behind your closed eyes. A barred spiral, a wheel of stars, a quiet home in the vastness. The journey continues when you are ready, and not a moment before. The journey continues when you are ready, and now we have arrived at a quiet pause where we can take one of the numbers that has come up again and again and hold it up to the light. That number is the light year. We have said that the Milky Way is about 100,000 light years across. We have said that our sun sits about 27,000 light years from the center. We have said that the nearest large galaxy, Andromeda, is about 2.5 million light years away. But what does that really mean, a light year? The name sounds like a measure of time because of the word year. But a light year is not a unit of time at all. It is a unit of distance. It is the distance that light travels in 1 year. That is the simple definition, and everything else we will say about it is just a way of letting that definition settle into the mind, slowly and calmly, until it feels like something you can hold. Let us begin with light itself. Light is fast. In the everyday world, light moves so fast that it might as well be instant. When you flip a switch on the wall, the room fills with light so quickly that you cannot perceive any delay at all. In a single second, a beam of light can travel around the entire Earth more than 7 times. Think about that for a moment. In the time it takes you to breathe in once, a particle of light could circle our whole planet again and again, racing across oceans and continents, looping the equator, and still have time left over. That is the speed of light in the vacuum of space, where there is no air to slow it down. It moves at about 186,000 miles in a single second. That number, written out in full, is 186,000 miles per second. In kilometers, it is about 300,000 kilometers per second. Those are big numbers for a single second of travel. The moon, which is the farthest place human beings have ever set foot, is about 240,000 miles away. Light covers that distance in a little more than 1 second. When the Apollo astronauts were on the moon, their radio signals, which travel at the speed of light, took about 1.25 seconds to reach Earth. There was a tiny delay in their conversations with mission control, a little gap of silence between a question and an answer, because the signal had to cross that gap of space at the speed of light. So light is fast, faster than anything else in the universe. Nothing we know of can move faster, but the universe is so large that even light's great speed is not enough to make the distances feel small. The stars are very far away. The space between stars is so vast that light, for all its speed, takes years to cross it. That is where the light year comes from. It is not a measure of time, though the word year is in it. It is a measure of how far light can go in the span of 1 Earth year, because the distances between stars are so huge that miles or kilometers become clumsy and hard to use. If we tried to measure the distance to the nearest star in miles, we would have to write out a number with so many zeros that the mind would simply refuse to hold it. The number would be around 25 trillion miles. That is 25 followed by 12 zeros. It is a number so large that it stops meaning anything in our everyday experience. We have no feel for trillions of miles. Our brains did not evolve to handle such spans. A light year takes that distance and wraps it up in a smaller, gentler package. Instead of saying 25 trillion miles, we can say 4 light years. That is the actual distance to the nearest star beyond our Sun, a star called Proxima Centauri. 4 light years. Light from Proxima Centauri takes 4 years to reach us. That means when you look at that star on a clear night, you are seeing light that left its surface 4 years ago. You are seeing the star as it was 4 years in the past. Let that idea rest for a moment. Light from the nearest star takes 4 years to get here. 4 years is a span of time we can feel. A child born when that light started its journey is now learning to walk and talk. A tree planted then is now a sapling. A whole season of life has passed on Earth while that beam of light raced across the emptiness, between stars at 186,000 miles every second, never slowing, never stopping, and it is only now arriving at your eye. That is the scale of a single light year multiplied by 4, and that is just the nearest star. The nearest one. The stars we can see with our bare eyes are scattered across distances of tens, hundreds, sometimes thousands of light years. The bright star Sirius, the brightest star in the night sky, is about 8.5 light years away. The light you see from Sirius tonight left that star 8.5 years ago. The star Betelgeuse, a red star in the constellation Orion, is about 500 light years away. Its light began traveling toward us around the year 1500, when the Renaissance was unfolding in Europe, long before anyone knew what a galaxy was. And the band of the Milky Way, that pale river of blended starlight, contains stars that are thousands of light years away, tens of thousands of light years away. The light from the center of our galaxy, 27,000 light years distant, left its source during the last ice age, when human beings were painting caves and living among mammoths and saber-toothed cats. This is the gentle strangeness of the light year. It is a measure of distance that is tied, by its very name, to time. Every time we say that something is a certain number of light years away, we are also saying something about how old the light is when it reaches us. We are saying that we see the object not as it is now, but as it was when the light began its journey. The farther away something is, the further back in time we are looking. This is not a metaphor or a trick. It is a straightforward consequence of light's finite speed. If the sun were to stop shining right now, at this very instant, we would not know it for about 8 minutes, because the sun is about 8 light minutes away. Light from the sun takes 8 minutes to cross the gap between the sun's surface and our planet. We live in a constant state of slight delay, receiving news of the universe only after the light has had time to travel. Now, for the distances inside our solar system, light minutes and light hours are enough. The sun is 8 light minutes away. Jupiter is usually between 30 and 50 light minutes away, depending on where it is in its orbit. The outermost planets are a few light hours away. But once we step beyond the solar system, the distances grow so fast that light days and light months quickly become too small to be useful. The nearest star is 4 light years away. The stars we see in the night sky range from a few light years to a few thousand light years away. Our galaxy as a whole is 100,000 light years across. And the nearest large galaxy, Andromeda, is 2.5 million light years away. 2.5 million years. The light from Andromeda that we see tonight began its journey when early human ancestors were walking the African savanna long before our species, Homo sapiens, even existed. That light has been traveling across the emptiness between galaxies for all of human prehistory and all of human history, through the rise of language and art and agriculture and cities, through every empire and every war and every act of love. And it is only now, tonight, brushing against the glass of a telescope or the retina of an eye. That is what a light year really means. It is a distance so large that it turns space into time. Let us slow down and build up the scale step by step, because it can help the mind settle into it. Imagine you are standing on a long, straight road. You have a flashlight. You turn it on for exactly 1 second, then turn it off. The light that left the flashlight in that 1 second is now racing away from you at 186,000 miles per second. After 1 second, the front edge of that beam of light is 186,000 miles away. That is a light second. It is a distance, not a time. It is how far light goes in 1 second. Now keep the flashlight on for a full minute. The beam stretches out to a distance of about 11 million miles. That is a light minute. Keep it on for an hour, and the beam reaches about 670 million miles. That is a light hour. Keep it on for a full day, and the beam stretches out to about 16 billion miles. That is a light day. Keep it on for a full year, 365 days, and the beam stretches out to about 6 trillion miles. That is a light year. 6 trillion miles. A 6 followed by 12 zeros. That is one single light year, and the nearest star is 4 of those away. The center of our galaxy is 27,000 of those away. The nearest large galaxy is 2.5 million of those away. The numbers stack up quietly, one after another, and the mind, quite rightly, stops trying to picture them and instead just accepts the feeling they create. The feeling of immense space, the feeling of deep time, the feeling of being very small in a very large room, but a room that is peaceful and dark and asks nothing of you. This is why astronomers use the light year. Not because it makes the distances small, but because it makes them sayable. It is easier to say, the Milky Way is 100,000 light-years across, than to say, the Milky Way is about 600,000 trillion miles across. Both statements are true, but one of them can be spoken calmly in the dark, and the other just sounds like a list of zeros. The light year folds the zeros into a unit that has a human scale at its heart. A year is something we understand. We have lived through years. We know the rhythm of a year, the turning of the seasons, the slow circle of the earth around the sun. Attaching that familiar span to a distance makes the distance feel not small, but at least approachable. We can say that light, moving at its impossible speed, takes a full year to travel 1 light year. That is a sentence we can hold. It gives us a handle on the vastness, a way to grip it without being crushed by it. And there is something calming in this. The light year tells us that the universe is old and large and slow, and that we are seeing it in layers of time. Every glance at the night sky is a glance into the past. The moon you see is about 1.25 seconds in the past. The sun is 8 minutes in the past. The planets are minutes or hours in the past. The stars are years, decades, centuries, millennia in the past. The galaxies are millions, even billions of years in the past. When you look at a distant galaxy through a telescope, you are looking at light that has been traveling toward you since before the Earth formed, since before the sun ignited, since the universe itself was much younger than it is now. The light year is a bridge between the very large and the very old, and crossing that bridge slowly, in the quiet of a dark room, can feel like drifting on a calm sea. There is no need to hurry. The light has already done all the traveling. You are just receiving it, here and now, as it arrives. So as we continue this journey, through the different shapes of galaxies and the mysteries of dark matter, and the quiet giants at galactic centers, we will use the light year again and again. We will say that a certain galaxy is so many million light years away. We will say that a certain cluster spans so many million light years across. And each time we say it, you can remember what it really means. It means distance. It means the slow crawl of light across the emptiness. It means that the object we are describing is being seen not as it is, but as it was, in some earlier chapter of the universe's long story. This is not a trick of perception, it is a basic fact of how light and space work together, and it is a fact that can settle around you like a soft blanket, because it places everything you see in a gentle, layered perspective. The universe is not a flat screen, it is a deep volume, filled with light of different ages, all arriving at your eye at the same moment, each photon carrying a different history, a different travel time, a different story from the past. So let the light year rest in your mind as we move forward. A light year is the distance light travels in 1 year. It is about 6 trillion miles. It is a way of making the immense numbers of astronomy sayable, holdable, almost gentle. It is also a way of understanding that every look into space is a look back in time. And it is the ruler we will use for the rest of this journey. When we say that Andromeda is 2.5 million light-years away, you will know that we are speaking of a distance so large that light, moving at 186,000 miles every second, takes 2.5 million years to cross it. When we say that the Milky Way is 100,000 light-years across, you will know that a beam of light would need 100,000 years to travel from one edge of our galaxy to the other. These are big thoughts, but they are calm thoughts. They are thoughts that put the troubles of the day into a wider frame, a frame so wide that it can hold anything, even the quiet drift towards sleep. The journey now moves on, into the forces that hold these great structures together. But the light year will travel with us, a quiet companion, a gentle measure, a way of holding the unholdable. The journey now moves on into the forces that hold these great structures together. We have talked about the shape of the Milky Way, its great spinning disk of stars, its curling arms, its quiet bar across the middle. We have talked about the distances involved, the light years that stack up into the tens of thousands and the hundreds of thousands. But there is a question that sits quietly behind all of this description. What holds a galaxy together? Why does it not simply fly apart? A galaxy is a vast collection of stars, each one moving in its own orbit around the center, at speeds that are hard to grasp. With so much motion, with so much mass in motion, what keeps the whole thing from scattering into the dark, like a handful of sand thrown into the wind? The answer, in one word, is gravity. But gravity, as we will see, carries a mystery within it, a quiet puzzle that scientists have been sitting with for many decades. Let us begin with what we can see. A galaxy contains stars, hundreds of billions of stars, each one a massive ball of glowing gas. These stars all pull on one another. Every star in the Milky Way exerts a gravitational tug on every other star. The sun pulls on the stars near the galactic center. Those stars pull back on the sun. The stars in the spiral arms pull on the stars in the bar. The whole system is a web of mutual attraction, a network of invisible threads connecting every point of mass to every other point. And it is not just the stars that do the pulling. A galaxy also contains gas, vast clouds of hydrogen and helium and other elements, spread throughout the disk. It contains dust, tiny grains of solid material, carbon and silicon and ice, that float between the stars and sometimes gather into thicker clouds that block the light. All of this material, every atom of gas and every grain of dust, has mass, and anything with mass exerts gravity. So the total gravity of a galaxy comes from all its visible parts added together. Stars, gas, dust, all pulling together, all holding the galaxy in a kind of gravitational embrace. This gravity is what gives the galaxy its shape. It pulls the material into a disk. It keeps the stars in their orbits. Without gravity, the stars would move in straight lines, flying off into intergalactic space, and the galaxy would dissolve in a cosmic instant. With gravity, the stars follow curved paths, circling the center in a slow and orderly dance. The gravity from all the visible matter is what keeps the Milky Way together, day after day, billion years after billion years. At least, that is what we might expect. That is what makes intuitive sense. If we could add up all the mass we can see and calculate how strong its gravity should be, we would expect the stars to orbit the center at certain speeds. The stars near the center, where the mass is densest, should orbit quickly. The stars farther out, where the mass thins out, should orbit more slowly. This is how gravity works in our solar system. The planets close to the Sun, like Mercury and Venus, orbit quickly. The planets far from the Sun, like Neptune and the distant dwarf planets, orbit slowly. The farther you are from the central mass, the weaker the pull, and the slower the orbit. It is a simple and beautiful pattern, and for a long time astronomers assumed that galaxies worked the same way. But when they began to measure the orbits of stars in other galaxies, and in our own Milky Way, they found something that did not match the simple picture. The stars far from the center were not orbiting more slowly. They were orbiting just as fast as the stars closer in. In some cases, they were orbiting even faster. The visible mass, the stars and the gas and the dust we can see, did not produce enough gravity to explain these high speeds. There had to be something else, something unseen, something that added extra gravity, extra pull, to hold the fast-moving stars in their orbits. If that extra gravity were not there, the outer stars would fly away. They are moving too fast for the visible mass to hold them, but they do not fly away. They stay in their orbits, calmly circling the center, just like the inner stars. So something is holding them, something invisible, something that does not give off light. This unseen something is what we now call dark matter. The name is carefully chosen. It is dark, not in the sense of being shadowy or sinister, but simply in the sense that it does not emit, absorb, or reflect light. It is invisible to our telescopes, not because our telescopes are weak, but because dark matter does not interact with light at all, as far as we can tell. It does not shine like a star. It does not glow like a cloud of hot gas. It does not block light like a cloud of dust. It is, in the most literal sense, transparent. We cannot see it directly. We can only infer its presence from the gravitational pull it exerts on the things we can see. The evidence for dark matter does not come only from the speeds of stars within galaxies. It comes from many different kinds of observations, all pointing to the same conclusion. When we look at clusters of galaxies, we see that the galaxies within those clusters are moving too fast to be held together by the visible mass alone. When we look at the way light bends around massive objects, an effect called gravitational lensing, we see more bending than the visible mass can account for. When we study the afterglow of the Big Bang, the faint radiation that fills all of space, we see patterns in that glow that are best explained by the presence of dark matter in the early universe. The case for dark matter is built from many independent lines of evidence, each one reinforcing the others. The picture is consistent and robust. There is more mass in the universe than we can see, a lot more. In a typical galaxy like the Milky Way, dark matter outweighs the visible matter by something like 5 or 6 to 1. That means that for every pound or kilogram of stars, gas, and dust, there are roughly 5 or 6 pounds or kilograms of dark matter, invisible and mysterious, surrounding the galaxy and permeating it. This dark matter is not just a thin sprinkling. It forms a vast, diffuse halo around the galaxy, extending far beyond the visible disk. The stars and gas of the Milky Way sit inside a much larger cloud of dark matter, like a bright yolk inside a transparent egg. This dark matter halo is what provides the extra gravity that keeps the outer stars in their orbits. It is what holds the galaxy together more tightly than the visible mass alone ever could, and it is not unique to our galaxy. Every spiral galaxy that has been measured shows the same pattern. Every large galaxy seems to have its own dark matter halo, a cocoon of invisible mass that shapes and steadies the visible structure within. Now, at this point in the telling, it would be easy to slip into a dramatic tone, a hidden mystery, an invisible universe, but that is not the spirit of this journey. The true spirit is much calmer. Dark matter is a mystery, yes, but it is a known mystery. It is a puzzle that scientists have been working on quietly and patiently for decades. They have ruled out many possible explanations. They have narrowed the search. And they continue to look without urgency or alarm, because the universe is not in a hurry, and neither are they. The not knowing is part of the calm. We do not need to solve dark matter tonight. We do not need to solve it at all. We can simply acknowledge that it is there, a quiet presence, a gravitational backdrop, an unseen companion to all the light we see. What might dark matter be made of? The honest answer is that we do not yet know. We know what it is not. It is not made of ordinary atoms, the kind that make up stars and planets and people. It is not made of black holes or dead stars or cold clouds of gas. All of those possibilities have been examined, and found wanting. The leading idea is that dark matter consists of some kind of particle, a subatomic particle that has mass but interacts very weakly, or not at all, with ordinary matter and with light. Such particles would pass through us constantly, billions of them every second, without us ever noticing. They would pass through the Earth as if it were not there. They would drift through the galaxy in vast, slow clouds, exerting their quiet gravitational pull, but never colliding, never clumping into solid objects, never forming anything as dense and visible as a star. This is the best guess we have, and it is a guess grounded in careful theoretical work and experimental searches, but it is still a guess. The true nature of dark matter remains one of the great open questions of astronomy, and that is perfectly fine. Science is not a collection of finished answers. It is a process of asking questions and refining them over time. Dark matter is a question that has been refined over many decades, from a vague suspicion to a tightly defined problem. We know there is something there. We know roughly how much of it there is. We know how it is distributed around galaxies and clusters. We just do not know what it is made of. And until we do, the question sits there, quietly, waiting for the next piece of evidence, the next careful measurement, the next patient insight. There is no rush. The dark matter has been there for billions of years. It will still be there when we wake. So let us return to the idea of gravity, the invisible glue. Gravity is what holds a galaxy together. That much is simple and true. The stars pull on each other. The gas pulls on the stars, the dust pulls on the gas, and underneath it all, unseen but deeply felt, dark matter pulls on everything. It is the hidden scaffolding of the galaxy, the unseen frame around which the visible structure is built. Without dark matter, the Milky Way might never have formed at all. The early universe was a soup of gas and radiation, with small ripples of density here and there. Gravity pulled on those ripples, and the ones with more mass pulled harder. Dark matter, being the dominant form of mass, would have clumped together first, forming gravitational wells into which ordinary gas could fall. Those gas clouds then cooled and condensed and eventually formed stars. The first galaxies may have been built inside cocoons of dark matter, and the galaxies we see today may still be shaped by those ancient, invisible structures. This is a picture that is both humbling and soothing. Most of the mass in the universe is not the kind of stuff we can see or touch. Most of it is dark, quiet, and patient. It does not shine. It does not burn. It does not demand attention. It simply exerts its gentle pull, holding the visible universe in a steady embrace. When you look up at the night sky and see the stars of the Milky Way, you are seeing only a small fraction of what is actually there. The rest is invisible, but it is not absent. It is all around you, passing through you, holding you in its gravitational field, just as it holds the sun and the earth and the whole galaxy. You are swimming in an ocean of dark matter, and you would never know it except through the careful measurements of science. There is something deeply peaceful about that. The universe has a hidden dimension, a quiet layer of reality that we are only beginning to understand. And that hidden dimension is not threatening, it is not chaotic, it is simply there, steady and calm, doing what gravity does. The same gravity that holds the galaxy together also holds you to the Earth. It is the same force, the same gentle curvature of space, described by the same laws. The gravity of the Earth keeps you in your bed. The gravity of the Sun keeps the Earth in its orbit. The gravity of the Milky Way keeps the Sun in its long, slow path around the galactic center, and the gravity of dark matter keeps the whole galaxy from flying apart. It is a chain of connection, a hierarchy of embraces, from the very small to the very large. You are part of that chain, you are held by it, and as you lie here in the dark, you can let yourself feel that hold, not as a weight but as a reassurance. The same force that shapes galaxies is shaping your rest. The same invisible glue that binds the cosmos is binding you, gently, to the turning Earth. So that is the invisible glue, gravity from the visible matter and gravity from the dark matter working together to hold the great wheel of the Milky Way in its stately rotation. The stars orbit, the gas flows, the dark matter halo surrounds it all, silent and unseen, and the mystery of what that dark matter really is remains open, a calm question mark in the middle of our understanding. We do not need to answer it tonight. We can just let it be. The next part of our journey will take us into the different shapes that galaxies can take, beginning with the spirals, the category that includes our own Milky Way. We will look at what makes a spiral galaxy a spiral, and we will meet some of the other great spirals in our cosmic neighborhood. But for now, rest with the thought of gravity, the quiet force that never sleeps, holding everything in its patient web. Rest with the thought of gravity, the quiet force that never sleeps, holding everything in its patient web. And now, from that rest, we can begin to look outward at the different shapes that galaxies take. Not all galaxies are alike, just as not all clouds are alike, or not all trees in a forest. They come in patterns, in families of form, and the first family we will spend time with is the one we know best, the spiral galaxies. Our own Milky Way is a spiral, and so is our nearest large neighbor, the Andromeda Galaxy. Spirals are the ones we picture most often when we think of a galaxy. They are the pinwheels, the great luminous whirlpools of stars, and they are among the most beautiful structures in the universe. A spiral galaxy is defined by its shape. It has a flat, rotating disk of stars, gas, and dust. It has a central bulge, a dense and rounded cluster of older stars at the very middle, and it has arms, curling lanes of brighter material that wind outward from the center in a spiral pattern. These arms are what give the spiral galaxy its name and its distinctive look. They are like the arms of a pinwheel, or the swirl of cream stirred into coffee, frozen in place on a scale so vast that a single turn of the pattern takes hundreds of millions of years. The whole disk rotates, but the arms are not solid objects. They are more like waves of density, regions where stars and gas are packed a little more tightly together, and as the disk turns, these waves of density move through it, like ripples on a pond. Stars enter the arms, linger there for a time, and then move on. But new stars are born in the arms because the arms contain more gas and dust, the raw material for making stars. That is why the arms look brighter than the rest of the disk. They are lit up by young, hot, luminous stars that have recently formed from the dense clouds found there. These young stars burn bright and blue-white, and they trace the spiral pattern like glowing beads on a string. Between the arms, in the dimmer regions, the stars are generally older and redder, and less gas is available to make new ones. So when you look at a photograph of a spiral galaxy, the bright blue arms are places of creation. They are stellar nurseries, where gravity is pulling gas together into new suns, and where those new suns are shining for the first time, illuminating the clouds from which they were born. The darker lanes that often trace the inner edges of the arms are lanes of dust, thick enough to block the light of stars behind them, and the center, the bulge, glows with a warmer, yellower light, the combined shine of billions of older stars that have been circling there for most of the galaxy's life. The whole image is one of quiet order, a structure that has settled into a stable pattern over billions of years. Spiral galaxies come in a few different varieties, and it is worth naming them gently, just to give the mind a little more detail to hold. Some spirals have arms that wind out directly from the central bulge. These are called ordinary spirals. Others, like our Milky Way, have a bar of stars across the middle, and the arms attach to the ends of the bar rather than to the bulge itself. These are called barred spirals. The bar is thought to be a kind of channel, a way of funneling gas from the outer parts of the galaxy toward the center, where it can feed the central black hole or form new stars. Bars are common. More than half of all spiral galaxies show some kind of bar structure. The Milky Way's bar is modest but real, and it is one of the features that places us in the barred spiral category. There is a further gentle division among spirals, based on how tightly their arms are wound and how prominent the central bulge is. Some spirals have arms that are wound very tightly, close to the center, and a large, bright central bulge. These are called, in the quiet language of classification, Sa galaxies if they are ordinary spirals, or Espa if they are barred spirals. Some have arms that are more loosely wound, with a smaller bulge and more open, sprawling arms. These are called C or SBC galaxies, and some are in between, called SB or SBB. The Milky Way is generally thought to be somewhere in the middle, an SBB or perhaps an SBC, with a moderate bar and fairly open arms. Andromeda, our neighbor, is an ordinary spiral without a strong bar, of the SB type. These labels are not important to remember. They are just a way of saying that spirals, like snowflakes, show a range of variation within a common theme. What makes a spiral galaxy a spiral in the first place? The answer, like so much in astronomy, involves gravity and rotation. A spiral galaxy forms from a vast rotating cloud of gas and dark matter. As the cloud collapses under its own gravity, it flattens into a disk because of the rotation, much as a ball of pizza dough flattens into a disk when it is spun. The gas in the disk can radiate away its heat and settle into a thin plane, while the dark matter and the oldest stars remain in a more extended halo around it. Within the disk, small irregularities in the density of the gas can grow over time, amplified by the rotation, until they organize into the spiral pattern we see. The arms are not permanent structures in the way that a mountain is permanent. They are patterns that come and go, that wind up and reform, that are maintained by the gravity of the disk itself and by the constant cycle of star birth and star death. A spiral galaxy is not a static object. It is a dynamic, flowing system, a pattern sustained by motion and gravity over timescales that dwarf any human measure. Let us take a moment to picture a spiral galaxy from above. Imagine a great disk of stars, 100,000 light-years across, turning slowly in the dark. The light from the center is warm and golden, the light of old stars that have been shining for 10 billion years. From that golden center, 2 or more blue-white arms emerge, curling outward like the arms of a whirlpool. Along those arms, bright knots of pink and blue glow, where new stars are being born in dense clouds of gas. The arms trail behind the direction of rotation, so the whole galaxy looks like a great spinning wheel with its spokes bent backward by the motion. Dust lanes, dark and thin, trace the inner edges of the arms, silhouetted against the brighter light behind them. The spaces between the arms are not empty, but they are quieter, filled with older, dimmer stars, and a thinner scattering of gas. Around the whole disk, a faint halo of dark matter and ancient stars extends outward in every direction, invisible except for a few scattered globular clusters that orbit high above and far below the plane. This is the portrait of a spiral galaxy. It is a portrait of our own Milky Way, and of Andromeda, and of countless other galaxies scattered across the universe. One of the best-known spiral galaxies beyond our own is the Andromeda Galaxy, which we will meet more fully when we explore our galactic neighborhood. Andromeda is about 2.5 million light-years away, and it is the farthest thing you can see with your bare eye on a dark night. It appears as a faint, elongated smudge of light, and through a telescope it resolves into a magnificent spiral, tilted at an angle to our line of sight, so that we see it not quite face-on and not quite edge-on, but somewhere in between. Its disk spans about 220,000 light-years, making it somewhat larger than the Milky Way. It has a bright central bulge, delicate spiral arms traced by young blue stars, and a retinue of smaller satellite galaxies orbiting around it. It is, in many ways, a sibling to our own galaxy, a slightly larger sibling but one built on the same plan. There are other famous spirals, with names that sound like entries in a quiet catalogue. The Pinwheel Galaxy, also known as Messier 101, is a face-on spiral in the constellation Ursa Major, showing its arms spread wide like a celestial pinwheel. The Whirlpool Galaxy, Messier 51, is another face-on spiral, this one interacting with a smaller companion galaxy, its arms distorted by the gravitational encounter into sweeping, graceful curves. The Sombrero Galaxy, Messier 104, is a spiral seen nearly edge-on, so that its disk appears as a thin line of light, with a bright bulge in the center and a dark lane of dust cutting across it, giving it the look of a wide-brimmed hat floating in space. Each of these galaxies is a variation on the spiral theme, a reminder that nature works in patterns but never repeats itself exactly. Spiral galaxies are common, but they are not the most common type. That distinction belongs to the smaller galaxies we will meet in a later section, the dwarf galaxies. But spirals are the ones that catch our eye because they are large and bright and structured. They are the great cities of the universe, the metropolises of stars. And they are the galaxies most likely to host life, or so we might gently speculate, because they contain the right mix of heavy elements, stable orbits, and quiet neighborhoods like the Orion Spur, where a planet can circle its sun in peace for billions of years. We cannot know if there is life elsewhere in the Milky Way or in Andromeda. That is another of the calm unknowns. But we do know that we live in a spiral galaxy, and that our spiral galaxy has given us a safe home in one of its quiet arms, far from the dangerous radiation of the central bulge, far from the crowded stellar traffic of the major arms, in a place where the night sky is dark enough to see out into the wider universe. So let the image of a spiral galaxy rest in your mind as you drift. A flat, rotating disk, a central bulge of older stars, curling arms traced by young blue stars and glowing gas. A bar across the middle, perhaps, connecting the arms to the center. A halo of dark matter and ancient light surrounding it all. This is the shape of our home. This is the shape of Andromeda and the Pinwheel and the Whirlpool and so many others. It is a shape that seems to arise naturally from the laws of gravity and motion, a pattern that appears again and again across the cosmos. And yet each spiral is unique, with its own particular arrangement of arms, its own history of mergers and star formation, its own quiet story written in the light of billions of suns. As we move forward, we will meet the other great family of large galaxies, the ones that are not spiral at all. They are smooth and round, shaped like eggs or spheres, and they tell a different story about how galaxies live and grow. They are the elliptical galaxies, and they are the subject of our next quiet step. But for now, you can simply hold the spiral shape in your mind, turning slowly in the dark, and let it carry you closer to rest. The arms curl, the stars are born, the galaxy turns, and you are here, inside one of them, safe and warm and part of the pattern. The journey will continue when it is time. The journey will continue when it is time. And now that time has come to meet the other great family of large galaxies. We have spent time with the spirals, those graceful pinwheels of stars and gas, with their curling arms and their bright young star clusters and their quiet central bulges. But spirals are not the only shape a large galaxy can take. There is another family, just as common among the big galaxies, and in some places even more common. These are the elliptical galaxies. They are different from spirals in almost every way that a galaxy can be different, and yet they are built from the same basic materials, governed by the same quiet force of gravity, and they share the same deep history of the universe. An elliptical galaxy is, at its simplest, a smooth and rounded collection of stars. It does not have a flat disk. It does not have spiral arms. It does not have the dark lanes of dust or the glowing pink clouds of star-forming gas that make spirals so visually rich. Instead, it is shaped like a ball, or sometimes like a stretched egg, a three-dimensional oval that astronomers call an ellipsoid. That is where the name elliptical comes from. If you could hold an elliptical galaxy in your hand, it would feel like a smooth stone, a pebble worn round by time. Its stars are not arranged in any obvious pattern. They swarm around the center in orbits that are more random, more jumbled than the orderly circular orbits of a spiral disk. Some stars move in long, stretched-out loops. Others move in tighter, rounder paths. The whole thing is a great cloud of suns, held together by gravity, but without the flat, organized structure that characterizes a spiral. The light of an elliptical galaxy is also different from that of a spiral. When you look at a spiral galaxy, you see a range of colors. The arms are blue-white with young, hot stars. The bulge is golden with older, cooler stars. The dust lanes are dark. The gas clouds glow pink. An elliptical galaxy, by contrast, looks mostly one color. It is reddish or yellowish, the light of stars that are old and cool and have been shining for a very long time. Elliptical galaxies contain mostly old stars. They have very little gas and dust, the raw materials for making new stars. Star formation, the process of turning gas clouds into new suns, has largely stopped in most elliptical galaxies. The gas that was once there has either been used up long ago, or blown away, or heated so much that it cannot collapse into new stars. So the stars in an elliptical galaxy are generally ancient, born in the early days of the universe, and they have been shining quietly ever since, slowly reddening as they age. This lack of gas and dust gives elliptical galaxies a calm, settled quality. They are not bustling with the activity of new star birth. They are not churning with the cycle of stellar life and death that marks a spiral. They are quiet. They are at rest. The stars simply orbit, slowly and steadily, in their three-dimensional swarm, and the galaxy as a whole just drifts through space, looking much the same from 1 billion years to the next. If a spiral galaxy is like a busy city, full of construction and noise and new buildings going up, an elliptical galaxy is like an old, quiet town, where the buildings are ancient and the streets are calm, and nothing much changes from century to century. Elliptical galaxies come in a very wide range of sizes. Some are quite small, barely larger than the biggest globular clusters. These are called dwarf ellipticals, and they are among the most common galaxies in the universe, though they are faint and hard to see at great distances. At the other end of the scale, some elliptical galaxies are enormous, the largest galaxies known. These giant ellipticals can contain trillions of stars and stretch across more than 1 million light-years, 10 times the size of the Milky Way. They are often found at the centers of large galaxy clusters, sitting like calm, bloated kings in the middle of a court of smaller spirals and irregulars. The most massive elliptical galaxies are thought to have grown by swallowing other galaxies over billions of years, a process we will talk about more in a later section. They are the end result of a long history of mergers and collisions, the final product of galactic evolution in the densest parts of the universe. The shape of an elliptical galaxy is described by how stretched it is. Some are nearly perfect spheres. These are called E0 ellipticals, the roundest ones. Others are more elongated, shaped like a football or a stretched egg. These are given higher numbers, up to E7, which is the most elongated type. The classification is a quiet and simple one, based entirely on the apparent shape we see from our vantage point on Earth. It does not tell us everything about the galaxy's true three-dimensional form, because we are seeing it from one angle, but it gives a gentle way of sorting them. A round elliptical looks very different in a photograph from a stretched one, even though both are members of the same family. One of the best-known elliptical galaxies is a giant named Messier 87, or M87 for short. It sits at the center of the Virgo cluster, a large gathering of galaxies about 54 million light-years away. M87 is a supergiant elliptical, one of the largest galaxies in our region of the universe. It contains several trillion stars, and it stretches across nearly 1 million light-years. It has a huge population of globular clusters, those tight swarms of old stars that orbit around it by the thousands. And at its center, it holds a supermassive black hole that is one of the largest known, with a mass of several billion suns. This is the black hole whose shadow was imaged by the Event Horizon Telescope, the first direct image of a black hole ever obtained. That image, released in 2019, showed a fuzzy ring of light surrounding a dark central shadow, and it confirmed, in a very direct way, that these giant elliptical galaxies harbor quiet giants at their hearts. M87 is a calm and massive presence, and we will meet its central black hole again when we talk about the quiet giants that reside in the centers of galaxies. How do elliptical galaxies form? The leading idea, supported by much evidence, is that they are built through mergers. When two spiral galaxies collide, which is a slow and graceful process that takes hundreds of millions of years, the result can be an elliptical galaxy. The collision scrambles the orderly disks of the spirals. The gas is compressed and forms a burst of new stars, using up much of the raw material in a short time. The remaining gas may be blown out of the galaxy by the energy of all those new stars and their supernova explosions. What is left is a cloud of old stars, orbiting in random directions, without a disk, without arms, without much gas. The two spirals have become one elliptical. This process can happen again and again, with larger ellipticals swallowing smaller ones, growing ever bigger over cosmic time. The giant ellipticals at the centers of clusters are likely the product of many such mergers, a long and patient accumulation of mass that has been going on for most of the age of the universe. This merger story is not just a theory. We can see it happening. When we look out into the universe, we see pairs of galaxies in the process of merging. We see galaxies with distorted shapes, with long tails of stars pulled out by gravitational tides, with bursts of new star formation triggered by the collision. We see the aftermath, galaxies that look like ellipticals but still show faint shells or ripples of stars, the remnants of past mergers that have not yet fully settled. And we can simulate the process on computers, modeling the gravity of billions of particles and watching as two spiral disks fall together and transform into a single elliptical cloud. The simulations match the observations well. The merger hypothesis is as solid as anything in this field. This means that elliptical galaxies are, in a sense, the elders of the galaxy world. They are what happens when spirals grow old and collide and settle down. They are the final stage in a long life, the quiet retirement after a youth of star formation and a middle age of gentle spiral turning. Not every elliptical has the same history, of course. Some small ellipticals may have formed early in the universe and simply never had much gas to begin with. But the broad pattern holds. Spirals are galaxies that are still actively forming stars and maintaining their disk structure. Ellipticals are galaxies that have largely finished their star formation and have settled into a rounder, calmer, older shape. There is something deeply peaceful about an elliptical galaxy. If a spiral is a busy city, and an irregular is a village in the middle of a storm, an elliptical is a quiet meadow of stars. The stars are old and steady. There are no great outbursts of new light, no dramatic cycles of birth and death. Just the slow, random orbits of ancient suns, circling in a great swarm, held together by gravity and dark matter. The light from an elliptical is smooth and even, fading gently from a bright center to a dimmer edge, without the sharp features that mark a spiral. In a long-exposure photograph, an elliptical looks like a soft, luminous cloud, a patch of light that seems to glow from within. It is the most serene of all the galaxy types, and to look at one is to feel a sense of deep time, of ages passing without hurry, of a structure that has found its final form and will hold it for billions of years to come. So as you lie here in the dark, you can hold the image of an elliptical galaxy in your mind alongside the spiral. One is a pinwheel of creation, blue and gold, full of gas and new stars and curling arms. The other is a smooth ball of ancient light, red and steady, full of old stars and quiet orbits. They are different expressions of the same basic forces, gravity and time, working on the same basic materials, gas and dark matter. And they are connected, because one can become the other. A spiral that lives long enough and encounters another galaxy may, in the fullness of time, become an elliptical. The universe is always changing, but it changes so slowly that we can hold both forms in our minds at once, as snapshots from different stages of a long and patient story. Let your breathing slow as you picture an elliptical galaxy. See it as a soft, rounded glow in the dark, the color of a sunset that has faded to embers. There are no sharp edges, no bright blue knots, no dark dust lanes, just a smooth gradient of light, brightest at the center and fading into the blackness of space. Inside that glow are trillions of stars, each one a sun, many of them older than our own, many of them circled by planets that have seen eons come and go. The whole structure drifts through space, quiet and complete, asking nothing of the universe except to be left alone with its ancient light. And around it, in a vast halo, the dark matter that we cannot see holds it all together, as steady and patient as the stars themselves. This is an elliptical galaxy. It is another face of the cosmos, another shape that a gathering of stars can take. And in the next part of our journey, we will meet the galaxies that do not fit neatly into either the spiral or the elliptical families, the smaller, messier, more irregular gatherings that round out the census of the sky. And in the next part of our journey, we will meet the galaxies that do not fit neatly into either the spiral or the elliptical families, the smaller, messier, more irregular gatherings that round out the census of the sky. We have visited the grand spirals, with their sweeping arms and their bright young stars. We have visited the calm ellipticals, smooth and ancient, shaped like balls and eggs. But if you were to take a true census of the universe, if you were to count every galaxy down to the faintest and smallest, you would find that the most common type of galaxy is neither spiral nor elliptical. The most common type is the dwarf galaxy. And among the dwarfs and the not-quite dwarfs, there are galaxies that have no clear shape at all, galaxies that look ragged and torn and disordered. These are the irregular galaxies. Together, the irregulars and the dwarfs make up the great majority of galaxies in the universe, even though they are the ones we hear about least often. Let us begin with the irregular galaxies. An irregular galaxy is exactly what its name suggests. It is a galaxy without a regular shape. It is not a neat spiral with curling arms. It is not a smooth elliptical with a round or oval form. It is messy. It is lopsided. It may have clumps of bright stars here and there, patches of glowing gas, dark lanes of dust that wander across it without any obvious pattern. An irregular galaxy looks like a spiral that has been stirred with a spoon, or an elliptical that has been pulled apart by some outside force, or a cloud of gas and stars that never quite got organized in the first place. Irregular galaxies are often rich in gas and dust, the raw materials for making stars, and they frequently have active regions of star formation, glowing pink and blue with the light of new suns. But this star formation is not arranged into neat spiral arms. It is scattered in clumps and knots, wherever the gas happens to be densest. Why are irregular galaxies irregular? In many cases, the answer is gravity again, but gravity applied from the outside. An irregular galaxy is often a galaxy that has been disturbed by a close encounter with a larger neighbor. Imagine two galaxies passing near each other. Their mutual gravitational pull stretches and pulls at their shapes. The orderly disk of a small spiral can be warped and twisted. Gas can be pulled out in long streams. Stars can be scattered into new orbits. The result, after the encounter, is a galaxy that no longer looks like a neat spiral. It looks like a mess. It is an irregular. Over time, gravity may smooth it out again, but in the immediate aftermath, it is ragged and torn. Some irregulars may be the remnants of collisions between two small galaxies, the debris of a cosmic accident that has not yet settled into a new form. Others may simply be small galaxies that never had enough mass to organize into a disk or a smooth sphere. Without a strong central pull, the stars and gas just drift in a loose and shapeless cloud. There are two nearby irregular galaxies that are well known to astronomers and to anyone who has spent time under the dark skies of the southern hemisphere. They are the Large Magellanic Cloud and the Small Magellanic Cloud. These are small companion galaxies to our own Milky Way, visible to the bare eye as faint, cloudy patches in the night sky. They look like detached pieces of the Milky Way band, drifting apart from the main stream. The Large Magellanic Cloud is about 160,000 light-years away. The Small Magellanic Cloud is about 200,000 light-years away. Both are classified as irregular galaxies, though the Large Magellanic Cloud has a hint of a bar structure and a suggestion of a spiral arm, making it a kind of transitional object between an irregular and a proper barred spiral. Both are rich in gas and dust, and both are actively forming stars. The Large Magellanic Cloud contains one of the largest and brightest star-forming regions known, a vast glowing nebula called the Tarantula Nebula, which is so luminous that if it were as close to us as the Orion Nebula, it would cast shadows on the Earth at night. The Magellanic Clouds are a gentle reminder that irregular galaxies are not just distant abstractions. They are our neighbors. They are part of our own galactic story. They orbit the Milky Way, bound by its gravity, and they are slowly being pulled apart by that same gravity as they circle closer. Streams of gas and stars trail behind them and ahead of them, stretched out along their orbits like taffy. Eventually, in the fullness of cosmic time, they will be absorbed into the Milky Way. Their stars will join our galaxy's disk and halo. Their gas will add fuel to our galaxy's star formation. This is how large galaxies grow, by slowly consuming their smaller companions. It is a quiet, gradual process, without violence or drama, just the patient work of gravity over billions of years. Now let us turn to the dwarf galaxies. A dwarf galaxy is simply a small galaxy. It is defined by its size and its mass, not necessarily by its shape. Dwarf galaxies can be spiral, elliptical, or irregular in form, though most are either dwarf ellipticals or dwarf irregulars. What makes them dwarfs is that they contain far fewer stars than a galaxy like the Milky Way. While the Milky Way has somewhere between 100 billion and 400 billion stars, a dwarf galaxy might have only a few billion stars, or a few hundred million, or in the smallest cases, just a few million. A few million stars sounds like a lot, and it is a lot by human standards. But by galactic standards, it is tiny. A dwarf galaxy is like a small village compared to the great cities of the spirals and giant ellipticals. Dwarf galaxies are faint. Because they have fewer stars, they put out less light. This makes them hard to see at large distances. We know of many dwarf galaxies in our own local group, the small cluster of galaxies that includes the Milky Way and Andromeda. More than 50 galaxies in the local group have been identified, and most of them are dwarfs. They orbit the larger galaxies like moons around a planet, or they drift in the spaces between them. New dwarf galaxies are still being discovered, even in our own cosmic backyard. Some are so faint and so diffuse that they are barely brighter than the background sky, and it takes careful analysis of telescope images to pick them out from the foreground stars of the Milky Way. The fact that dwarf galaxies are the most common type in the universe is a calm and interesting truth. When we look at the big, bright spirals and ellipticals, we are looking at the celebrities of the galactic world. They are the ones that dominate photographs and capture the imagination. But they are not the typical galaxy. The typical galaxy is a small, faint dwarf, holding a modest number of stars, drifting quietly around a larger companion or sitting alone in the void. The universe is full of these small gatherings. They are the ordinary citizens of the cosmos, while the Milky Ways and Andromedas are the rare giants. Why are dwarf galaxies so common? The answer goes back to how galaxies form in the first place, a story we will explore more fully in the next section. In the early universe, gravity pulled together clumps of dark matter of all different sizes. The smallest clumps pulled in only a little gas and formed only a few stars before the gas was used up or blown away. The largest clumps pulled in enormous amounts of gas and formed the big galaxies we see today. The small clumps, the dwarfs, were far more numerous than the large ones. It is a pattern we see everywhere in nature. There are more pebbles than boulders. There are more villages than cities. There are more small trees than giant redwoods. The universe tends to make many small things and fewer large things, and galaxies are no exception. The smallest dwarf galaxies are so faint and so loosely held together that they blur the line between a galaxy and a mere star cluster. Some of the dwarf spheroidal galaxies orbiting the Milky Way contain only a few 100,000 stars, spread out over a few hundred light-years. They have so little mass that their stars are barely bound to each other by gravity. A slight nudge from a passing larger galaxy could scatter them, And yet, by definition, they are galaxies, because they contain dark matter. A star cluster, like a globular cluster, is held together only by the gravity of its visible stars. It has little or no dark matter. A dwarf galaxy, even a very small one, is embedded in a halo of dark matter that outweighs its stars many times over. That dark matter is what distinguishes a tiny galaxy from a big star cluster. It is the invisible signature that says, "This is a galaxy, a true gathering of the cosmos, not just a swarm of stars." Let us take a moment to picture one of these dwarf galaxies. Imagine a small, faint cloud of light, floating in the dark space near the Milky Way. It is perhaps a few thousand light-years across, a fraction of the size of our galaxy. It contains a few tens of millions of stars, a modest number compared to the hundreds of billions in the Milky Way. Its stars are old, mostly, because dwarf galaxies often used up their gas long ago and have not formed new stars for billions of years. They shine with a soft, reddish light. The stars are spread out thinly, so that if you lived on a planet inside a dwarf galaxy, your night sky would be very different from ours. You might see only a few hundred stars with your bare eye, not a few thousand. The Milky Way band would not be visible, because there is no dense disk of stars to form a band. Instead, you might look up and see the great spiral of the Milky Way itself, or the soft glow of Andromeda, dominating your night sky as external galaxies, beautiful and remote. The dwarf galaxy drifts quietly, bound by the gravity of its larger neighbor, slowly being stripped of its outermost stars as it orbits. It is a humble and peaceful existence, the life of a dwarf galaxy, a small gathering of suns in the vastness. The large and small Magellanic Clouds, which we mentioned earlier, are examples of dwarf irregular galaxies. They are relatively large for dwarfs, with the large Magellanic Cloud containing perhaps 30 billion stars. But they are still far smaller than the Milky Way, and they are irregular in shape because of their gravitational interaction with our galaxy. They are among the best-studied galaxies in the sky because they are so close and so bright. Astronomers use them as laboratories to study star formation, gas dynamics, and the effects of tidal forces. They are a gift, really. Two small galaxies right on our doorstep, where we can examine them in detail and learn about how galaxies work. So the picture of galaxies is now complete in its broad outlines. We have the spirals, with their flat disks and curling arms. We have the ellipticals, smooth and round and ancient. And we have the irregulars and the dwarfs, the small and the messy, the ones that do not fit the neat categories but are, in fact, the most numerous of all. These are the shapes that a gathering of stars can take. They are the forms that gravity and time produce when given gas and dark matter and billions of years to work. Each one is unique, and yet each one belongs to a family. The classification is not a cage. It is a gentle way of seeing patterns in the diversity. As you lie here in the dark, you can let these shapes drift through your mind like clouds. A spiral, turning slowly, an elliptical, glowing softly, a dwarf, faint and humble, an irregular, ragged and full of new stars. They are all out there, in their billions and trillions, scattered across the observable universe. They are not still images in a book. They are dynamic, evolving systems, moving and changing over timescales so vast that we can only glimpse a single frame of their long lives. But even that glimpse is enough. It is enough to know that we live in one of them. A spiral, a barred spiral, a galaxy of moderate size and quiet disposition. And it is enough to know that our galaxy has neighbors, some large and some small, some shapely and some shapeless, all held together in a small cluster that we will visit soon. The next part of our journey will shift from what galaxies are to how they came to be. We will trace their story back to the early universe, to the slow gathering of gas and dark matter that built the first protogalaxies, and we will follow that story forward through billions of years of mergers and growth. But for now, you can rest with the census we have taken. Spirals, ellipticals, irregulars, dwarfs. A taxonomy of light, a quiet list of the ways that stars can gather. The universe is full of them, and you are inside one, and that is a gentle thought to carry into sleep. The stars drift, the galaxies turn, the dark holds them all, and you are part of it, quiet and small and perfectly at home. The stars drift, the galaxies turn, the dark holds them all, and now we can ask a gentle question. Where did all these galaxies come from? Not just our own Milky Way, but the spirals and the ellipticals and the irregulars and the dwarfs, the whole great census of light. How did they begin? How did they grow into the shapes we see today? This is a story that takes us back to the very early universe, to a time when there were no galaxies at all, only a vast and simple sea of gas and dark matter, slowly stirring under the pull of gravity. In the beginning, as far as we can tell, the universe was very nearly smooth. After the Big Bang, which is the name we give to the moment when the universe began expanding from an extremely hot and dense state, space was filled with a nearly uniform soup of particles and radiation. There were no stars. There were no planets, there were no galaxies, there was just a thin, hot fog of hydrogen and helium gas, with a trace of lithium, and a background of dark matter particles moving slowly through the expanding space. But this soup was not perfectly smooth. There were tiny ripples, small variations in density from place to place. Some regions were a little denser than average, others were a little less dense. These ripples were incredibly small, variations of perhaps 1 part in 100,000. But they were there, imprinted on the universe from its earliest moments. Gravity worked on these ripples. In the denser regions, gravity pulled inward a little more strongly than in the less dense regions. Over millions of years, these slight overdensities grew. The dark matter, which feels gravity but does not interact with light, began to clump together into loose, diffuse clouds. These clouds of dark matter became the seeds of future galaxies. They were the gravitational wells into which ordinary gas would later fall. Think of them as invisible bowls, slowly taking shape in the dark, waiting to be filled with the hydrogen and helium that would one day become stars. As the universe expanded and cooled, the gas, which had been too hot to do anything but bounce around, cooled enough to fall into those dark matter bowls. It settled there, pooling in the gravitational wells, growing denser and denser. Within these pools of gas, smaller clumps began to form. The densest parts of the gas clouds collapsed under their own gravity, heating up as they contracted, until the temperature and pressure at their centers became high enough to ignite nuclear fusion. The first stars turned on. They were massive and bright and short-lived by cosmic standards, burning through their fuel in just a few million years, and then exploding as supernovae. These first stars enriched the surrounding gas with heavier elements, the carbon and oxygen and iron that are forged in stellar cores. This enriched gas then cooled and formed a second generation of stars, and a third, and so on. The process was gradual and cumulative. Over hundreds of millions of years, the first protogalaxies took shape. They were smaller than the Milky Way, probably irregular in form, messy and turbulent with bursts of star formation and supernova explosions. They were the building blocks of the larger galaxies to come. These small protogalaxies did not stay separate for long. Gravity brought them together. Because they were massive, they attracted one another. Clumps of dark matter and gas and young stars began to merge, pulled together by their mutual gravitational pull. When two protogalaxies collided, their gas clouds slammed together, triggering new waves of star formation. Their dark matter halos merged into a larger halo. Their stars, which were too far apart to collide directly, mingled together to form a larger stellar system. Over time, through a long sequence of such mergers, larger galaxies were built. This is the picture that astronomers call hierarchical galaxy formation. The small things formed first, and then they combined to make larger things. Dwarf galaxies merged to make medium-sized galaxies. Medium-sized galaxies merge to make large galaxies. The process is still going on today, though at a slower pace than in the early universe, because the universe has expanded and the galaxies have grown farther apart. The Milky Way itself carries the scars of this history. It has not been a closed system, forming in isolation and remaining unchanged. It has grown by absorbing smaller galaxies. When we look closely at the Milky Way, we see streams of stars that are not in the main disk or the central bulge. These stellar streams are the remains of smaller galaxies that wandered too close and were torn apart by the Milky Way's gravity. They are like the bones of past meals, scattered in long trails across the halo. One well-known stream is called the Sagittarius stream, the stretched-out remains of a dwarf galaxy that passed through the Milky Way's disk and is being slowly shredded. The stars from that dwarf galaxy now wrap around the Milky Way in a great looping ribbon, gradually mixing into our galaxy's stellar population. The Magellanic Clouds, which we met in the last section, are in the process of being absorbed. They are still largely intact, but streams of gas and stars trail behind them and ahead of them, pulled out by the Milky Way's tidal forces. In a few billion years, they too will be fully consumed, and their stars will become part of our galaxy's disk. This process of merging is not a violent catastrophe in the way we might imagine. It is slow. It unfolds over hundreds of millions or billions of years. The galaxies approach each other at speeds that are fast by human standards, but leisurely on the cosmic scale. Their mutual gravity distorts their shapes, pulling out long tails of stars and gas. They may pass through each other several times before finally settling into a single system. The stars themselves almost never collide because the distances between them are so vast. Even when two galaxies pass right through each other, their stars stream past one another like two flocks of birds crossing paths in the sky. The gas is different. Gas clouds do collide, and these collisions compress the gas and trigger bursts of star formation. This is why some merging galaxies show bright regions of new star clusters, glowing pink and blue in the midst of the gravitational chaos. We can see galaxy mergers happening all around us, at various stages, simply by looking out into the universe with telescopes. Some galaxies appear close together, their shapes distorted into long arcs and tails. Some show double nuclei, two bright centers where the cores of two galaxies have not yet fully merged. Some are surrounded by shells and ripples of stars, the fading echoes of past mergers. And some are in the final stages of merging, looking like a single galaxy, but with an oddly disturbed shape that tells of a recent union. Astronomers have catalogued many such systems, and they provide a kind of time-lapse view of the merger process. By studying galaxies at different stages of interaction, we can piece together the whole story, from first approach to final settling. The largest elliptical galaxies, the giant ones at the centers of rich clusters, are likely the end products of many, many mergers. Over the history of the universe, a galaxy sitting at the center of a cluster has had countless opportunities to absorb smaller galaxies that fell into its gravitational well. Each merger added mass. Each merger scrambled the orbits of the stars, helping to turn any disk into a more spherical shape. Each merger used up gas in bursts of star formation, leaving less fuel for future generations of stars. The result, after billions of years, is a giant elliptical, smooth and old and gas-poor, a monument to a long history of galactic cannibalism. Our own Milky Way, if it merges with Andromeda in the distant future, as we will discuss in a later section, may end up as part of a larger elliptical galaxy. The quiet spiral we know today is not the final form. It is a stage in a longer story. So galaxies are born from small seeds of dark matter and gas in the early universe. They grow by pulling in more gas from their surroundings and by merging with other galaxies. They shape themselves into spirals if they have a steady supply of cool gas and can form a rotating disk. They become ellipticals if they undergo major mergers that scramble their disks and use up their gas. They become irregulars if they are disturbed by neighbors or if they are too small to organize into a neat shape. The whole process is one of slow, patient assembly, driven by gravity and regulated by the physics of gas and stars. It is a story that has taken more than 13 billion years to unfold, and it is still unfolding. The universe is not finished. New stars are still being born. New galaxies are still forming from the gas that remains. Old galaxies are still merging and evolving. The cosmic story is ongoing, and we are in the middle of it, not at the end. There is something deeply calming about this picture. It places our existence in a flow of time that is almost incomprehensibly vast. The galaxy we live in is not a static object, fixed and eternal. It is a living system, with a birth and a history and a future. The stars we see in the night sky are part of that history. Some of them were born in other galaxies, long since absorbed. Some of them are ancient, nearly as old as the universe itself. Some are young and hot, formed recently from gas that has been cycling through the Milky Way for eons. The atoms in our bodies were forged in stars that lived and died in this galaxy, or in smaller galaxies that merged with it. We are made of recycled starlight, of elements that have been through multiple generations of stars and supernovae, scattered across space and gathered again by gravity. The story of galaxies is, in a very real sense, our own story. It is the prehistory of our own existence. Let us pause here, and let this long story settle. In the beginning, a nearly smooth sea of gas and dark matter. Tiny ripples of density, growing under gravity. Dark matter clumping into invisible bowls. Gas falling into those bowls, cooling, forming the first stars. Small proto-galaxies taking shape, merging and growing over billions of years. Spiral disks forming where gas could cool and settle. Ellipticals taking shape where mergers scrambled the order. Dwarfs and irregulars filling in the gaps. And through it all, the quiet, patient pull of gravity, the same force that holds you to your bed tonight, shaping the largest structures in the universe. The next part of our journey will turn outward from our own galaxy to meet our nearest neighbors. We will step from the Milky Way into the small cluster of galaxies that surrounds us, the local group, and we will get to know our largest companion, the Andromeda Galaxy. But for now, you can rest with the story of how galaxies are born and grow. It is a story without a final chapter, a story that will continue long after our sun has burned out and our Earth is gone. New galaxies will form, old galaxies will merge. The universe will keep unfolding, calm and slow and beautiful, as it has for more than 13 billion years. And you, in this moment, are a part of that unfolding, a tiny conscious piece of a vast and patient cosmos. Let that thought hold you, gentle and steady as you drift. Let that thought hold you, gentle and steady as you drift. And now, from the long story of how galaxies are born and grow, we can turn our attention outward to the immediate surroundings of our own Milky Way. We have spent time inside our galaxy, learning its shape and its size and its quiet structure. But the Milky Way is not alone. It does not drift through the universe in complete isolation. It has neighbors. It belongs to a small, calm cluster of galaxies, a little family of stellar gatherings, bound together by gravity. This is our galactic neighborhood, and its name, in the quiet language of astronomy, is the local group. The local group is a collection of galaxies. It is not a large collection, not one of the great clusters that contain thousands of members. It is a modest group, a scattering of perhaps 50 or 60 known galaxies, maybe a few more that we have not yet detected. Most of these galaxies are small and faint. They are the dwarf galaxies we talked about earlier, the tiny villages of stars that orbit the larger members like moons around a planet. The local group has three main members, three galaxies that dominate the scene by their size and their mass. The first is our own Milky Way. The second is the Andromeda Galaxy, our largest neighbor. And the third is a spiral galaxy called the Triangulum Galaxy, smaller than the other two, but still a proper spiral, with a disk and arms and a central bulge. These three are the giants of the local group, and everything else orbits around them or drifts in the spaces between. Let us begin with Andromeda, because Andromeda is the Milky Way's closest large companion and the most distant object visible to the bare human eye. On a very dark night, far from city lights, You can see Andromeda as a faint, elongated smudge in the constellation of Andromeda, near the great square of Pegasus. It is not a star. It does not twinkle like a star. It is a soft patch of light, and that soft patch of light is the combined glow of roughly 1 trillion stars. Andromeda is a spiral galaxy, like the Milky Way, but it is somewhat larger. Its disk stretches about 220,000 light-years across, compared to the Milky Way's 100,000 light-years. It has a bright central bulge, delicate spiral arms traced by young blue stars, and a retinue of its own satellite galaxies, including 2 prominent dwarf ellipticals that orbit it closely. It is, in many ways, a sibling to our own galaxy, a slightly larger sibling built on the same basic plan. Andromeda lies about 2.5 million light-years from us. That is the distance we have mentioned several times in this journey, and now we can sit with it in the context of our neighborhood. 2.5 million light-years. The light we see from Andromeda tonight left that galaxy 2.5 million years ago, long before modern humans walked the Earth. That light has been traveling across the emptiness between galaxies at 186,000 miles per second, never slowing, never stopping, and it is only now arriving in our telescopes and our eyes. On the scale of the universe, 2.5 million light-years is not very far. It is just a few times the diameter of the Milky Way itself. Galaxies are large relative to the spaces between them, much larger in proportion than stars are relative to the spaces between stars. If the Milky Way were a dinner plate, Andromeda would be another dinner plate about 25 plate widths away. On a cosmic scale, that is close. It is close enough that the 2 galaxies feel each other's gravity. They are bound to each other, part of the same small gravitational system. Andromeda and the Milky Way are not sitting still relative to each other. They are moving. Measurements of Andromeda's light show that it is blue-shifted, which is the technical term for light that is compressed, because the source is moving toward us. Most distant galaxies are red-shifted, moving away from us because of the expansion of the universe. But Andromeda is close enough that the expansion of the universe is overcome by the mutual gravitational attraction between it and the Milky Way. The 2 galaxies are falling toward each other. Their current closing speed is about 250,000 miles per hour, or about 110 kilometers per second. That is fast by earthly standards, but on the scale of 2.5 million light-years, it is a very slow approach. At that speed, it will take about 4.5 billion years for the 2 galaxies to meet. 4.5 billion years. That is a span of time comparable to the current age of the Earth. When Andromeda and the Milky Way finally begin to merge, the Sun will still be shining, though it will have grown somewhat brighter over the eons. The Earth, if it still exists as a planet, will likely be uninhabitable by then, due to the Sun's increasing heat, a separate and much earlier problem. But the merger itself will not be a catastrophe for any individual stars or their planets. As we discussed in the section on how galaxies grow, galaxy collisions are not like car crashes. The stars are so far apart that they almost never hit each other. The 2 galaxies will pass through each other, their stars streaming past one another in a slow, gravitational dance. Their shapes will be distorted. Long tails of stars and gas will be flung out into space. Bursts of new star formation will light up the merging clouds. And eventually, after perhaps 1 billion years of swirling and settling, the 2 galaxies will merge into a single, larger galaxy. Some simulations suggest the result will be a giant elliptical galaxy, lacking the neat spiral structure of its 2 progenitors. Some astronomers have already given this future merged galaxy a name. They call it Milky Way, a gentle blend of the 2 names. This is the future of our galactic neighborhood. It is a calm future, a slow future, one that will unfold over timescales that dwarf any human concern. There is no need to worry about it. There is no need to do anything about it. It is simply what will happen in the fullness of deep time as gravity does its patient work. The merger of Andromeda and the Milky Way is a well-supported prediction, based on careful measurements of the galaxy's motions and masses. It is as certain as any forecast can be, on a timescale of billions of years. And it is, in its own way, a beautiful thing to contemplate. Two great spirals, each containing hundreds of billions of stars, drifting together across the void, meeting and mingling and becoming something new. The third major member of the local group is the Triangulum galaxy, also known as Messier 33. Triangulum is a spiral galaxy, smaller than both the Milky Way and Andromeda. It contains perhaps 40 billion stars, and its disk spans about 60,000 light-years. It is located about 3 million light-years from us, a little farther than Andromeda, and it is visible with binoculars, or a small telescope in the constellation Triangulum. Triangulum is notable for its open, loosely wound spiral arms and its active regions of star formation. It has a beautiful face-on orientation, which makes it a favorite target for astrophotographers. It is also a companion to Andromeda, orbiting the larger galaxy much as the Magellanic Clouds orbit the Milky Way. Triangulum may or may not be involved in the future merger between Andromeda and the Milky Way. Depending on its orbit, it might join the merger later, or it might swing around and merge with the combined galaxy in an even more distant future. The details are uncertain, but the broad picture is clear. The galaxies of the local group are slowly drawing together, and over the next many billions of years, they will coalesce into a single, larger system. Beyond the three main spirals, the local group contains a quiet population of smaller galaxies. There are more than 50 known members, and more are still being discovered. Most of these are dwarf galaxies, too faint to see with the bare eye. They have names like the Leo the First Dwarf, the Sculptor Dwarf, the Fornax Dwarf, and the Ursa Minor Dwarf. They are small, containing only a few million to a few 100 million stars. They orbit the larger galaxies like satellites, or they drift in the spaces between them. Some of them are so faint and diffuse that they were only discovered in the last few decades, using sensitive digital detectors on large telescopes. There are likely more still waiting to be found, hiding in the glare of the Milky Way's disk, or simply too dim to have been noticed yet. The local group is not a random scattering of galaxies. It has a structure. The Milky Way and its satellites form one subgroup, centered on our galaxy. Andromeda and its satellites, including Triangulum, form another subgroup, centered on Andromeda. These two subgroups are the main concentrations of mass, and they are slowly falling toward each other. The whole local group spans a region of space about 10 million light-years across. That is a large volume by any human measure, but on the cosmic scale, it is a small and cozy neighborhood. The galaxies within it are bound together by their mutual gravity. They are not flying apart with the general expansion of the universe. They are a little island of gravitational togetherness in the larger cosmic sea. This is an important point and worth pausing on. The universe as a whole is expanding. Distant galaxies are moving away from us, and the farther they are, the faster they recede. This is the phenomenon known as the expansion of the universe. But within a group or cluster of galaxies, the expansion is overcome by gravity. The galaxies are close enough and massive enough that their mutual pull holds them together against the general outward flow. The local group is one such bound system. It will not be torn apart by cosmic expansion. It will stay together, and eventually its members will merge. This is true of all galaxy groups and clusters. They are islands of stability in the expanding universe, held together by the quiet persistence of gravity. Let us take a moment to picture our local group from above, as if we were floating far outside it and looking down on its arrangement. Imagine a dark volume of space, about 10 million light-years across. In one part of this volume, the Milky Way shines, a barred spiral with its two bright dwarf companions, the Magellanic Clouds, and a swarm of fainter dwarf galaxies in orbit around it. About 2.5 million light-years away, Andromeda shines a little more brightly, a larger spiral with its own retinue of satellites, including the Triangulum galaxy off to one side. The space between these two main subgroups is not empty. It contains a few scattered dwarf galaxies, small and faint, drifting in the gravitational no man's land between the two larger systems. And around the whole arrangement, a vast cloud of dark matter, far larger than the visible galaxies themselves, holds everything in its gentle gravitational grip. This is our neighborhood. This is the local group. It is a quiet, small, and ordinary collection of galaxies, one of many similar groups scattered across the universe. The local group is not the largest structure we belong to. It is itself part of something larger, a supercluster of galaxies that we will explore in a later section. But it is the most immediate context for our galactic existence. When we look out into the night sky and see the faint smudges of other galaxies, we are seeing members of our own local group, or perhaps a few galaxies just beyond its borders. The Andromeda Galaxy is the brightest of these. The Triangulum Galaxy is another. The Magellanic Clouds, visible only from the southern hemisphere, are part of our own Milky Way's satellite system. These are our cosmic neighbors, our fellow travelers in the dark. They are the other villages and towns in our small corner of the universe. There is something comforting about knowing our neighbors. We have spent so much of this journey looking inward at our own galaxy, and outward at the vast census of galaxy types, and backward in time to the birth of the first galaxies. Now we can rest in the present, in the actual arrangement of galaxies that surrounds us. We are not alone in the void. We are part of a small family, a little cluster of stellar cities and stellar villages, bound together by gravity and drifting slowly toward a common future. The Milky Way and Andromeda, the two big sisters of the local group, are moving toward each other across 2.5 million light-years of empty space. Triangulum watches from a little farther away. The dwarf galaxies orbit quietly, patient and faint, and all of it is held together by the same invisible glue, the dark matter that we cannot see, but whose gravitational influence we can measure and map. So as you lie here in the dark, you can place yourself in this neighborhood. You are on a planet, circling a star, in the Orion spur of the Milky Way. The Milky Way is a barred spiral, about 100,000 light-years across. It is part of a small group of galaxies called the local group, which spans about 10 million light-years. Its largest companion, Andromeda, is visible on a dark night as a faint smudge, a patch of light that is the accumulated glow of 1 trillion stars. That light has traveled 2.5 million years to reach you, and in a few billion years, the two galaxies will merge, and the night sky will change in ways we can only imagine. But that is a story for the distant future. For now, you can simply rest in the knowledge of where you are, here and now, in this quiet neighborhood, among these quiet companions. The journey will continue soon, into the heart of our galaxy and the quiet giant that lives there. But for now, the local group drifts, and you drift with it, held by gravity, held by the dark, held by the calm. The journey continues now, into the heart of our galaxy and the quiet giant that lives there. We have traveled outward from the Milky Way to its shape, its size, its neighbors, and the broader families of galaxies. Now we turn inward, toward the very center of our galactic home, to a place that is both dense with stars and dominated by a single, invisible presence. This is the quiet giant at the center. It is a black hole, and not just any black hole, but a supermassive one, an object whose gravity shapes the inner regions of the Milky Way, and whose nature is both well-measured and deeply mysterious. Let us begin by stepping carefully toward the idea of a black hole. The term itself can sound dramatic, but the reality, as we understand it, is simply a region of space where gravity is so strong that nothing, not even light, can escape. A black hole forms when a very large amount of matter is squeezed into a very small volume. The gravity at the surface of such a concentrated mass becomes so intense that the speed needed to break free from it exceeds the speed of light. Since nothing can travel faster than light, nothing can leave. The boundary around the black hole, the point of no return, is called the event horizon. It is not a solid surface. It is just the line in space where the escape velocity equals the speed of light. Once anything crosses that line, it cannot come back. It is lost to the outside universe forever. Black holes come in different sizes, Some are formed when a very massive star runs out of fuel and collapses under its own weight. These are called stellar mass black holes, and they typically contain a few times to a few tens of times the mass of our Sun. The Milky Way probably contains millions of such black holes, scattered throughout its disk, remnants of stars that lived fast and died young. But the black hole at the center of the galaxy is of a different order entirely. It is not a few times the mass of the Sun. It is millions of times the mass of the Sun. This is what we mean by a supermassive black hole. Supermassive black holes are found at the centers of most large galaxies, not just our own. They are a standard feature of galactic architecture, as common as central bulges and dark matter halos. The one in the Milky Way has a name. It is called Sagittarius A star, often written as Sagittarius A with an asterisk, and pronounced Sagittarius A star. The name comes from its location. If you look toward the constellation Sagittarius, you are looking toward the center of the Milky Way. The galactic center lies about 27,000 light-years away in that direction, hidden from our direct view by thick clouds of dust that block visible light. But radio waves and infrared light can pass through that dust, and when astronomers pointed radio telescopes at the galactic center, they found a bright, compact source of radio emission. They called the overall region Sagittarius A. Within that region, they identified a very small, very bright point source, and they named it Sagittarius A star. That point source, that tiny spot of radio light, is the location of the supermassive black hole at our galaxy's heart. How do we know it is a black hole? We cannot see the black hole itself. It is, by definition, dark. No light escapes from inside the event horizon, but we can see the effect it has on the stars and gas around it. For decades, astronomers have been tracking the motions of individual stars in the very center of the galaxy. These stars orbit an invisible point at tremendous speeds. One star, called S2 or sometimes S02, completes an orbit around Sagittarius A star once every 16 years. By measuring the shape and size of its orbit and the orbits of other stars nearby, astronomers can calculate the mass of the unseen object they are all circling. That mass comes out to be roughly 4 million times the mass of our Sun, and it is packed into a volume so small that no other known object could fit there except a black hole. A cluster of normal stars or stellar remnants would be far larger and would glow brightly. A single object with that much mass in that small a space can only be a black hole. The evidence for this has been gathered patiently over many years, using large telescopes equipped with special instruments that can correct for the blurring of the Earth's atmosphere. The stars at the galactic center move. They trace out their elliptical orbits, whipping around the invisible central point at speeds of thousands of kilometers per second. Their motions are a direct demonstration of the black hole's gravity. The data fits the predictions of general relativity, Einstein's theory of gravity, with remarkable precision. There is no reasonable doubt. At the center of the Milky Way, about 27,000 light-years from where you are lying right now, there is a supermassive black hole with a mass of about 4 million suns. 4 million solar masses is a large number, but it is worth putting it in perspective. The black hole is enormous by the standards of any single star, but it is tiny compared to the galaxy as a whole. The Milky Way has a total mass, including dark matter, of roughly 1 trillion solar masses. The central black hole accounts for only a tiny fraction of that, about 4 millionths of the total. Its gravity dominates the orbits of stars very close to it, within a few light-years of the center. But farther out, the gravity of the galaxy's stars, gas, and dark matter takes over. The black hole is the anchor of the galactic center, but it is not the master of the whole galaxy. The Milky Way is not a solar system writ large, with everything orbiting a single central mass. The galaxy is a collective, a community of stars held together by their mutual gravity and by the dark matter halo. The black hole is just one member of that community, the densest and most extreme member, but not the one that holds everything else in thrall. This is true of supermassive black holes in general. They are central, but they are not all-powerful. Their gravitational reach extends only so far. The galaxy beyond that inner region is governed by the distributed mass of stars, gas, and dark matter. The black hole is a quiet giant, sitting at the heart of the system, exerting its influence on its immediate surroundings, but leaving the outer disk and halo to their own slow dance. In the year 2022, the Event Horizon Telescope, a worldwide network of radio observatories that work together as a single instrument, released an image of Sagittarius A star. This was the second image ever made of a black hole's immediate surroundings, after the first image of the black hole in the galaxy M87, released in 2019. The image of Sagittarius A star shows a fuzzy ring of radio light surrounding a dark central shadow. The ring is not the event horizon itself, which is too small to see directly. It is the light from hot gas swirling around the black hole, bent and magnified by the black hole's extreme gravity. The dark shadow at the center is the region where light cannot escape, the imprint of the event horizon on the surrounding glow. The image is a little blurry because the source is small and distant and the observations push the limits of what is technically possible. But it is a direct confirmation, a portrait of the quiet giant taken from 27,000 light-years away. The image matches what general relativity predicted. The size of the shadow is consistent with a black hole of 4 million solar masses. It is a settled fact, a known thing, and it can rest calmly in our understanding without fanfare. What happens at the very center of a black hole? This is where the calm of our knowledge gives way to honest mystery. Inside the event horizon, the known laws of physics break down. General relativity, which describes gravity so well everywhere else, predicts that all the matter that falls into a black hole is crushed into a point of infinite density called a singularity. At that point, space and time as we know them cease to exist. But most physicists believe that a singularity is not a real physical object. It is a sign that the theory is incomplete, that general relativity cannot handle the extreme conditions at the black hole's center. To describe what truly lies there, we would need a theory that unifies gravity with quantum mechanics, the physics of the very small. Such a theory does not yet exist, despite decades of effort by some of the brightest minds in science. We do not know what is at the center of a black hole. We may never know, because the event horizon hides it from any possible observation. This not knowing is not a failure. It is simply where the frontier of understanding currently sits. It is a calm, open question, a place where science is still working, patiently, without rush. So we can say that at the center of our galaxy, there is a supermassive black hole called Sagittarius A star. Its mass is about 4 million times that of the Sun. It is surrounded by a cluster of stars that orbit it at high speed. It occasionally flares in brightness when a bit of gas or dust falls into it and heats up. Most of the time it is quiet, quiescent, barely luminous at all. It is not a monster consuming everything around it. It is a sleeping giant, a calm presence at the heart of the Milky Way. The stars near it orbit safely, as long as they keep their distance. The black hole does not reach out and grab things. Its gravity is strong, but it is not a cosmic vacuum cleaner. If the Sun were replaced by a black hole of the same mass, the Earth and the other planets would continue in their orbits unchanged, because the gravity at their distance would be exactly the same. Only very close to the event horizon does the extreme gravity produce strange effects. So as you lie here in the dark, you can picture the center of our galaxy, 27,000 light-years away, in the direction of the constellation Sagittarius, hidden behind curtains of dust. There, stars swarm in a dense cluster around an invisible point. One of those stars, S2, comes within 17 light-hours of the black hole at its closest approach, and then swings out on a long ellipse, taking 16 years to complete a single orbit. The black hole itself is utterly dark, but around it, hot gas glows in X-rays and radio waves, tracing a swirling disk and a faint ring of bent light. The mass of 4 million suns is concentrated into a volume smaller than the orbit of Mercury. The gravity there is fierce, but contained. Beyond a few light years, the galaxy's other gravity takes over, and the spiral arms wind outward, and the disk rotates, and we, out here in the Orion Spur, orbit the center in our own slow, 230 million year circle. The black hole is part of the galaxy, a central part, but the galaxy is far more than its center. The Milky Way is a whole, a community, a gathering, and at its heart, a quiet giant rests, holding its small court of close stars, a point of deep mystery that we are only beginning to understand. There is no need to solve that mystery tonight. The black hole will be there, patient and dark, long after we have finished this journey. What matters now is simply the knowing. We know it is there. We know its mass and its location. We have seen its shadow. And we know that what lies inside its event horizon is, for now, beyond our grasp. That is a peaceful place to end this section. A supermassive black hole, 4 million times the mass of the Sun, sits at the center of our galaxy. It is called Sagittarius A star. It is quiet most of the time. It holds its secrets close. And we, out here in the disk, orbit it from a safe and comfortable distance, 27,000 light-years away, in the calm suburbs of a barred spiral galaxy. The journey now will widen its view again, from the single quiet giant at our own center to the larger structures that galaxies build together, the clusters and the cosmic web. But for now, rest with the image of that dark point, that calm mystery, that quiet giant at the heart of home. The journey now widens its view again, from the single quiet giant at our own center to the larger structures that galaxies build together. We have met our local group, the small cluster of galaxies that contains the Milky Way, Andromeda, Triangulum, and their retinue of dwarf companions. But the local group is not the whole story. It is just one small neighborhood in a much larger city. Galaxies, it turns out, are not scattered randomly across the universe. They gather. They form clusters and groups and vast superclusters, all connected by the patient pull of gravity. And on the largest scales we can observe, these clusters and superclusters are themselves arranged in a pattern, a web of filaments and sheets and great empty voids. This is the architecture of the universe at its grandest scale. This is the cosmic web. Let us step outward from the local group, slowly and gently. The local group spans about 10 million light-years and contains a few dozen galaxies. That sounds large, and it is, but it is small compared to what comes next. The local group is not isolated. It is part of a much larger gathering of galaxies called the Virgo Supercluster. A supercluster is a collection of galaxy groups and clusters, all bound together by gravity, spread across hundreds of millions of light-years. The Virgo supercluster contains at least 100 groups and clusters, with thousands of individual galaxies in total. Its center is dominated by a rich cluster called the Virgo cluster, which lies about 54 million light-years away in the direction of the constellation Virgo. The Virgo cluster is a true metropolis of galaxies. It contains more than 1,000 known member galaxies, maybe as many as 2,000. Most of them are dwarf ellipticals, but there are also many spirals and a few giant ellipticals at the center. The largest of these is Messier 87, the supergiant elliptical we met in the section on elliptical galaxies, the one with the enormous central black hole whose shadow was imaged in 2019. The Virgo cluster is the gravitational heart of our supercluster. The local group is just a quiet suburb, orbiting far out on the edges, slowly being pulled toward that dense center over billions of years. The Virgo supercluster is enormous. It stretches across about 110 million light-years. That means if you could travel at the speed of light, it would take you 110 million years to cross from one side to the other. The local group is just a tiny dot within this vast structure, a small clump of galaxies about 54 million light-years from the center. The supercluster contains so much mass, both visible and dark, that its gravity shapes the motions of galaxies across a huge volume of space. Galaxies that are not part of the supercluster are generally moving away from us with the expansion of the universe. Galaxies within the supercluster have their motions modified by the supercluster's gravity. They flow toward the densest regions, attracted by the combined pull of all the other galaxies and dark matter. The idea of a supercluster is a gentle one. It means that even large clusters of galaxies are not the final level of organization. There is another level above that, a level where clusters themselves group together into larger families. The Virgo supercluster is one of many superclusters scattered across the observable universe. It is not the largest and it is not the smallest. It is an ordinary supercluster in an ordinary part of the cosmos, and it is our home in the widest sense. When we give our cosmic address in full, we say that we live on Earth, in the solar system, in the Orion spur of the Milky Way, in the local group, in the Virgo supercluster. That is the full line, from the ground to the largest structure we can call our own. But even superclusters are not the end of the story. When astronomers map the positions of galaxies across the entire observable universe, they see something remarkable. Galaxies and clusters and superclusters are not arranged randomly. They form a pattern. They are arranged in long filaments, thin sheets, and dense knots, with vast empty regions in between. This pattern looks, to the human eye, like a web. It is called the cosmic web. The filaments are like threads, stretching across hundreds of millions of light years, made of galaxies and gas and dark matter. The knots are the rich clusters and superclusters, where many filaments intersect, and the voids are the empty spaces between the filaments, regions where very few galaxies are found. Some voids are hundreds of millions of light years across, nearly devoid of bright galaxies, though they may contain faint dwarf galaxies or diffuse gas that we have not yet detected. The cosmic web is the largest pattern we have ever observed. It is the structure of the universe on the grandest possible scale. It is not a solid structure, of course. The filaments are not rigid. They are just regions where the density of galaxies is higher than average, strung out along lines that trace the underlying distribution of dark matter. The pattern formed from those tiny ripples in the early universe that we talked about in the section on how galaxies are born and grow. Those ripples, amplified by gravity over billions of years, grew into the web we see today. The densest regions became clusters and superclusters. The moderately dense regions became filaments. The least dense regions became voids, emptying out as their matter flowed toward the denser regions. The whole thing is a gravitational network, a map of where the mass is and where it is not. Let us try to picture this, not as a diagram, but as a place. Imagine you could float far, far outside the Virgo supercluster, so far that the whole supercluster looks like a small, bright patch in the darkness. From this vantage point, you would see other superclusters scattered around you, each one a concentration of thousands of galaxies glowing faintly. Between them you would see the filaments, chains of smaller groups and clusters, strung like beads on invisible strings. The filaments would stretch away in various directions, connecting the superclusters into a loose network. And between the filaments you would see the voids, dark and nearly empty, vast bubbles of space, where the density of galaxies is very low. The whole scene would be still and quiet, a frozen snapshot of a structure that is actually evolving, but so slowly that a human lifetime would perceive no change at all. This is the universe in which we live. It is a universe of patterns, of organization on the largest scales. Galaxies are not alone. They are social creatures. They gather into groups. Groups gather into clusters. Clusters gather into superclusters. And superclusters are woven into the cosmic web. At every level, gravity is the force that builds these structures, pulling mass together over billions of years. And at every level, dark matter is the hidden scaffolding, providing most of the mass that drives the gravitational pull. The visible galaxies are just the luminous tips of vast dark matter icebergs, tracing out a structure that is mostly invisible. One of the largest known structures in the observable universe is called the Hercules Corona Borealis Great Wall. It is a filament of galaxies so large that it challenges our sense of scale. It stretches across about 10 billion light-years. That is more than a tenth of the diameter of the observable universe. It contains countless galaxies, clusters, and superclusters, all strung out along a single gravitational thread. The existence of such large structures is consistent with our current understanding of the universe, but it pushes against the limits of what we expect. There is some debate about whether the Great Wall is a true physically bound structure or just a chance alignment. That debate is part of the ongoing quiet work of cosmology. It is a reminder that even on the largest scales, there are things we are still figuring out. Another well-known structure is the Laniakea supercluster, which is the supercluster that contains the Virgo supercluster and many others. Laniakea is a Hawaiian word meaning immense heaven. It was identified by mapping the motions of galaxies and finding the boundary where galaxies are flowing toward one gravitational center versus another. Laniakea contains about 100,000 galaxies and stretches across about 520 million light-years. Its center is a region called the Great Attractor, a dense concentration of mass that is pulling the local group and many other groups toward it. The Great Attractor lies beyond the Virgo cluster, in a direction that is partly obscured by the dust of the Milky Way's disk. We cannot see it directly with visible light, but radio and X-ray telescopes have revealed a massive cluster of galaxies there, adding its gravity to the Virgo clusters and drawing everything in the region toward it. The cosmic web is the final answer to the question of what the universe looks like on the largest scales. It is not a uniform soup of galaxies. It is not a single giant explosion with galaxies flying outward. It is a network, a foam, a web of light and mass stretching across the void. And it is beautiful, in a quiet and mathematical way. The pattern is fractal-like, meaning that similar shapes appear at different scales. Stars gather into galaxies, galaxies gather into clusters, clusters gather into superclusters, superclusters gather into filaments. At each level, gravity builds structures that are clumpy and filamentary, leaving voids behind. It is a pattern that arises naturally from the physics of the early universe and the relentless pull of gravity over cosmic time. What holds all of this together? The same forces we have been talking about all along. Gravity, mostly from dark matter, is the architect. Dark energy, a separate mystery we will touch on in the next section, is the force that is accelerating the expansion of the universe, pushing the voids to grow emptier and the filaments to stretch. Together, dark matter and dark energy are the two great invisible players in the cosmic story. One pulls together, the other pushes apart. And between them, they have shaped the universe into the web we see. As you lie here in the dark, you can let your mind drift up through these scales, from your bed to the Earth, to the solar system, to the Milky Way, to the local group, to the Virgo supercluster, to Laniakea, to the cosmic web itself. Each level contains the ones below it, and is contained by the ones above it. You are at the bottom of a nested set of structures, each one larger and more ancient than the last, and all of it is held together by the same quiet gravity that holds you to the earth. The same force that shapes the cosmic web shapes your rest. You are not separate from this grand architecture. You are inside it. You are made of its stuff. Your body contains atoms forged in stars that lived and died in galaxies, that are now part of clusters, that are now part of the web. The connection is direct and physical. The iron in your blood once floated in the gas of the Virgo cluster. The calcium in your bones was synthesized in a supernova that lit up a filament of the cosmic web billions of years ago. You are the universe, in a very literal sense, looking at itself. So rest now with the image of the cosmic web, filaments of galaxies stretching across the dark, vast voids, silent and nearly empty, clusters and superclusters, glowing faintly with the light of trillions of stars. And somewhere in one small filament, in one small supercluster, in one small group, there is a barred spiral galaxy, and in one of its quiet arms there is a yellow star, and around that star there is a blue planet, and on that planet there is you, lying in the dark, listening to these words. You are part of the web. You always have been. You always will be. The atoms will rejoin the cosmos, and the web will continue to evolve, long after this moment is gone. But this moment is here now, and it is peaceful, and it is yours. The journey will continue soon, into the things we still do not know, the honest mysteries that remain. But for now, the cosmic web holds you, and you can let it. The journey continues now into the things we still do not know, the honest mysteries that remain. We have traveled a long way together through the quiet dark. We have visited the shape of our own galaxy, traced its spiral arms, measured its light years, and stood at the edge of the quiet giant at its center. We have met the other galaxies, the spirals and the ellipticals and the irregulars and the dwarfs, and we have seen how they gather into clusters and superclusters and the great cosmic web. We have talked about dark matter, the invisible glue that holds it all together, and through all of this we have tried to be honest about what we know and what we do not know. Now, before we come to the final rest, we should pause and give the not knowing its proper space, because there is much we do not know, and that is not a problem to solve or a gap to fill. It is simply where we are. It is the calm, open horizon of human understanding. Let us begin with a question that seems simple. How many galaxies are there in the universe? We have talked about the billions of stars in a single galaxy and the billions of galaxies in the observable universe. But how many, exactly? The honest answer is that we do not know. We do not even know the number to within a factor of 10. Estimates vary widely, from about 200 billion to as many as a few trillion. That is a large range. 200 billion is a 2 followed by 11 zeros. A few trillion is a few followed by 12 zeros. Why is the number so uncertain? The reason is that most galaxies are small and faint, far too dim to see with even our best telescopes. The universe is vast, and light from distant galaxies has been traveling for billions of years, growing fainter and redder as space itself expands. The most distant galaxies appear to us as tiny red smudges, barely brighter than the background sky. Many smaller galaxies, the dwarf galaxies that we know are the most common type, are simply invisible at large distances. We can only count the ones we can see, and then we must estimate how many more there are that we cannot see. This estimation is done by looking at a small patch of sky, a tiny square of the dark, and counting every galaxy in that patch, down to the faintest detectable limit. Then that number is multiplied by the total area of the sky. But the patch is small, and the faintest galaxies are right at the edge of detection. Different telescopes, different instruments, and different methods of counting give different results. The number also depends on what we count as a galaxy. Where is the dividing line between a very small galaxy and a large star cluster? That line is fuzzy. Some of the faintest smudges we see may be galaxies that are no longer forming stars, so dim that they are almost invisible. Others may be fragments of larger galaxies torn apart by mergers. The census is still being taken, and it will be refined over time. For now, the number is somewhere between 200 billion and a few trillion. That uncertainty is not a failure. It is just the current state of a difficult measurement. Science is still working on it, patiently, and the answer will sharpen as telescopes improve and methods advance. Now let us turn to dark matter. We have spoken about it several times in this journey. It is the invisible mass that surrounds galaxies and holds them together. Its gravity is essential to the structure of the universe. But what is it made of? After decades of study, after many experiments and observations, the honest answer is that we still do not know. We know what it is not. It is not made of ordinary atoms, the kind that make up stars and planets and people. If it were, we would see its effects in other ways. It is not made of black holes or dead stars or cold clouds of gas. All those possibilities have been examined and ruled out. The leading hypothesis is that dark matter is made of some new kind of particle, a particle that has mass but interacts very weakly, perhaps only through gravity, with ordinary matter. Such particles are often called WIMPs, which stands for weakly interacting massive particles. That name is just a placeholder, a way of saying that we have a category in mind, but we have not yet filled it with a specific discovery. Many experiments have been built to detect these hypothetical particles. They are placed deep underground, shielded from cosmic rays and other interference, waiting for the rare moment when a dark matter particle might bump into an ordinary atomic nucleus and produce a tiny flash of light or heat. So far, no confirmed detection has been made. Other experiments have searched for signs of dark matter particles annihilating each other in space, producing gamma rays or other radiation that we could detect with telescopes. So far, no clear signal has been found. The search is ongoing. It has been ongoing for decades. It may continue for many more decades. It is a calm and methodical search, not a desperate one. The dark matter is there. We can measure its gravitational effects. We just do not know what it is made of. And until we do, the question sits quietly on the table, one of the great open puzzles of modern science. There are other ideas about dark matter that go beyond the particle hypothesis. Some scientists have wondered whether our theory of gravity itself might need to be modified. Perhaps what we interpret as extra mass is actually a change in how gravity works on very large scales. This idea is called modified gravity, and it has been explored in various forms. But so far, the evidence from galaxy clusters and the cosmic microwave background, the afterglow of the Big Bang, strongly favors the dark matter particle hypothesis over modified gravity. The debate is not settled, but the weight of evidence leans heavily toward dark matter being real, physical stuff, not just a flaw in our equations. Still, until the stuff itself is detected directly, a sliver of uncertainty remains, and that uncertainty is part of the honesty of science. We hold our conclusions with the strength that the evidence warrants, but we remain open to new evidence, new ideas, new ways of understanding. Beyond dark matter, there is another mystery, even deeper and less understood. It is called dark energy. The name is a label for something we know almost nothing about. Dark energy is the term we use for whatever is causing the expansion of the universe to accelerate. We have known since the late 1990s that the universe is not just expanding, but that the expansion is speeding up. Galaxies are moving away from each other faster and faster as time goes on. This was a surprising discovery, because gravity should be slowing the expansion down. All the mass in the universe pulls on all the other mass, and that mutual pull should act as a brake on the outward motion. But observations of distant supernovae, exploding stars of a particular type that can be used as distance markers, showed that the expansion is not slowing. It is accelerating. Something is pushing space apart. That something is what we call dark energy. The name dark is used in the same way as in dark matter, not meaning sinister, but meaning unknown and invisible. Dark energy does not seem to clump like dark matter does. It appears to be spread evenly throughout space, a kind of background property of the vacuum itself. In the equations of general relativity, it is possible to add a term called the cosmological constant, which was originally introduced by Einstein and later discarded, then revived when the acceleration was discovered. The cosmological constant would act as a kind of repulsive force, a gentle outward pressure that counteracts gravity on the largest scales. Dark energy might be that cosmological constant, or it might be something else, a dynamic field that changes over time. We do not know. What we do know is that dark energy is the dominant component of the universe. According to the best current measurements, the universe is made of about 68% dark energy, 27% dark matter, and only about 5% ordinary matter, the stuff we are made of, the stuff that makes up stars and planets and galaxies and people. All of the visible universe, everything we have ever seen with our telescopes, everything we have talked about in this long journey, is just 5% of what is out there. The other 95% is dark, in one form or another. Dark matter holds the galaxies together. Dark energy pushes the universe apart, and we do not know what either of them really is. That sounds like it should be a dramatic revelation, but it is not. It is just a fact, a calm and measured fact. It is where the evidence has led us. Science is a process of asking questions and following the evidence wherever it goes. Sometimes the evidence leads to a clear answer. Sometimes it leads to a deeper mystery. Dark matter and dark energy are deeper mysteries. They are the current frontier. They are the questions that the next generation of telescopes and experiments and theorists will work on, quietly and patiently, just as the last generation worked on the questions that we have now answered. The not knowing is not a cause for alarm, it is a cause for continued curiosity, and it is perfectly fine to rest with these unknowns, to let them be unsolved, to let them drift in the back of the mind like faint galaxies in a deep field image. Let us return to the question of how many galaxies there are, because it connects to this larger theme of not knowing. The number of galaxies in the observable universe is uncertain, not just because of counting difficulties, but because we do not know how many small, faint galaxies formed in the early universe. Theoretical models based on dark matter simulations predict that there should be many more small galaxies than we actually see. This is called the missing satellite problem, or the dwarf galaxy problem. Our own Milky Way should have hundreds of small satellite galaxies, according to the simulations, but we only see a few dozen. Where are the missing ones? They might be there but too faint to see. They might have formed, but then been torn apart by the Milky Way's gravity, their stars scattered into the halo. They might never have formed stars at all, remaining as dark clumps of pure dark matter with no visible component. We do not know. The missing satellite problem is another item on the list of things we are still figuring out. It is not a crisis. It is a puzzle, and puzzles are what scientists work on, day by day, year by year, without rush. Then there is the question of what happens at the center of a black hole, which we touched on in the section about the quiet giant. General relativity predicts a singularity, a point of infinite density where space and time break down. Most physicists believe that a singularity is not a real physical thing, but a sign that the theory has reached its limit. To describe what truly lies there, we need a theory of quantum gravity, a theory that merges the physics of the very large, general relativity, with the physics of the very small, quantum mechanics. We do not have such a theory yet. String theory and loop quantum gravity are two candidates, but neither is complete or experimentally verified. The center of a black hole is a place where our current understanding stops. We do not know what is there. We may never know, because the event horizon hides it from any possible observation. That is a profound not knowing, and it may be a permanent one. And yet, we can hold that not knowing calmly. We can acknowledge it, respect it, and let it be. These are the big open questions. How many galaxies are there? What is dark matter made of? What is dark energy? What happens inside a black hole? There are many others, smaller but no less interesting. How did the first galaxies form exactly? And when did the first stars turn on? What is the fate of the universe? Will it expand forever, growing colder and darker? Or will the expansion someday reverse? Or will dark energy change over time and produce some other outcome? These are questions that the next decades of astronomy will address, with new telescopes and new instruments and new ideas. And the answers, when they come, will likely raise new questions. That is the rhythm of science. It is not a path toward a final, complete understanding. It is a path of deepening inquiry, where each answer opens onto new unknowns. And that is not a flaw. It is the nature of the enterprise. The universe is vast and subtle, and our minds are small and finite. We will never know everything. We will always have mysteries to sit with, and that is a beautiful thing, not a sad one. So as you lie here in the dark, nearing the end of this journey, you can let these unknowns drift around you like the faintest stars in the deepest sky. They are not gaps to be feared. They are invitations to continued wonder. They are the quiet assurance that the universe is not a closed book, but an open one, with pages still to be written. You do not need to solve these mysteries. You do not need to understand them fully. You can simply know that they exist, and that patient people are working on them, and that the work will continue long after tonight. The dark matter will still be there, invisible and patient. The dark energy will still be pushing space apart, gently and steadily. The black holes will still be hiding their singularities behind their event horizons. The count of galaxies will still be uncertain, an estimate with error bars, a number that shifts slightly with each new deep field image. And all of that is fine. It is all part of the calm. The next and final section of our journey will take us back to where we began, to the night sky and the quiet dark, but now carrying everything we have learned. We will drift into the scale of it all, and then we will let go, and let sleep come. But for now, rest with the not knowing. It is as much a part of the cosmos as the stars themselves. And now we have arrived at the final quiet stretch of our journey. This is the moment when we return to where we began, to the night sky and the quiet dark, but we return carrying something we did not have when we set out. We carry the knowledge of what lies behind each point of light. We carry the shape of our own galaxy, the names of its neighbors, the scale of its distances, and the honest mysteries that remain unsolved. All of that has settled into us, not as a burden but as a soft and steady presence. And now we can let it all drift, like leaves on a slow river, as we ease toward the stillness at the end. Remember the very first image we called to mind. A warm night, far from any city. The ground beneath you, solid and steady. The sky above, deepening from blue to indigo, to a darkness so pure it seems almost liquid. And then the stars, one by one, pricking through the dark. The longer you looked, the more you saw. That sky has not changed. It is still there, above the roof, above the clouds, above the atmosphere. It is there even now, in the middle of the day, hidden by the glare of the sun. The stars do not go away. They simply wait. And now, when you picture that sky, you can feel the depth behind it. Every star you imagine is a sun, some larger and brighter than our own, some smaller and dimmer. And every faint smudge beyond the stars, every little patch of haze that is not a cloud, is a galaxy. A gathering of billions of suns, a city of stars, turning slowly in the dark, held together by gravity. You know now that our own sun is part of such a gathering. It belongs to the Milky Way, a barred spiral galaxy about 100,000 light-years across. It sits in a quiet arm, the Orion Spur, about 27,000 light-years from the center. It is one star among somewhere between 100 billion and 400 billion. It is not special in its size or its brightness or its position. It is ordinary, and yet it is ours. It is the star that warms our planet, that drives our weather, that makes the grass grow and the oceans shimmer. It is the star that gives us day and night, summer and winter, the steady rhythm of the seasons. And it is held, like all the other stars, by gravity. The same gravity that shapes the spiral arms of the Milky Way, that holds the dark matter halo in place, that keeps the supermassive black hole at the center, surrounded by its tight swarm of orbiting stars. That same gravity holds you to the Earth, holds the Earth in its orbit, holds the Sun in its long, slow path around the galactic center. Gravity is the thread that runs through everything, from the smallest pebble to the largest supercluster. It is the quiet force that never sleeps, and it is holding you right now, as you lie here in the dark, as gently and as steadily as it holds the stars. You know now that the Milky Way is not alone. It has companions. The Magellanic Clouds, visible from the southern hemisphere, are small, irregular galaxies that orbit our own, slowly being pulled apart by our gravity. Andromeda, the great spiral 2.5 million light-years away, is our largest neighbor, visible as a faint smudge to the bare eye on a dark night. Andromeda and the Milky Way are moving toward each other, falling together across the void, and in about 4.5 billion years they will merge, their stars mingling in a slow and graceful dance that will eventually produce a larger, rounder galaxy. The Triangulum Galaxy, smaller and more distant, watches from the outskirts. And all around these main players, dozens of dwarf galaxies orbit quietly, too faint for the eye to see, part of the same small family called the local group. The local group itself is just one modest cluster within the Virgo supercluster, which contains thousands of galaxies across more than 100 million light-years. And the Virgo supercluster is just one branch of the cosmic web, the great network of filaments and voids that spans the entire observable universe. All of this is above you, around you, within you. The elements that make up your body were forged in stars that lived and died in this galaxy, or in smaller galaxies that merged with it long ago. The iron in your blood, the calcium in your bones, the oxygen that fills your lungs with every slow breath, all of it was cooked in the furnaces of ancient suns and scattered across space when those suns ended their lives. Gravity gathered that scattered stardust into clouds, and the clouds collapsed into new stars and new planets, and on one of those planets, the third one out from a yellow star in the Orion spur, that stardust arranged itself into living things. You are not separate from the galaxy. You are a piece of it, a conscious piece, a piece that can look up at the night sky and wonder. You are the Milky Way, looking at itself. That is not poetry, or not only poetry. It is a plain fact, established by decades of careful science. The atoms in your left hand may have come from a different star than the atoms in your right hand. We are all made of recycled starlight, gathered and regathered over billions of years, shaped by gravity and time into this moment, this breath, this quiet awareness. And there are things we still do not know. That is all right. The dark matter that holds the galaxy together remains unidentified. The dark energy that pushes the universe apart is even less understood. The total number of galaxies in the observable universe is uncertain, somewhere between 200 billion and a few trillion. What lies at the center of a black hole is hidden behind an event horizon, beyond the reach of current physics. These are not problems you need to solve. They are not gaps to be filled before you can rest. They are simply the current edge of our understanding, the horizon where our knowledge fades into calm mystery. Science is still working, patiently, as it always has. New telescopes will be built, new observations will be made, new theories will be proposed and tested. The work will continue, year by year, decade by decade. But you do not need to wait for those answers. You can rest now, in the middle of the questions, and let them be. The universe does not require us to understand it in order to be beautiful. It does not require us to solve it in order to be peaceful. It simply is, and we are part of it, and that is enough. So now, as we drift into the final stillness, let the images come one last time, soft and slow. Picture the night sky, the one we began with, the one people have looked up at for all of history. See the stars, the few thousand bright points that are our closest neighbors in the galaxy. See the Milky Way band, the pale river of light that is the blended glow of billions of distant suns in the disk of our galaxy. See the faint smudges, the patches of haze that are other galaxies, each one a separate gathering of billions of stars, each one turning slowly in the dark. See Andromeda, the brightest of them, its light 2.5 million years old, arriving at your eye after a journey that began before modern humans walked the Earth. See the local group, the small cluster of galaxies bound by gravity, drifting together in a quiet corner of the Virgo supercluster. See the Virgo supercluster itself, a vast aggregation of groups and clusters, containing thousands of galaxies, stretching across 110 million light-years. See the cosmic web, the filaments and voids, the largest pattern in the universe, the network of dark matter and galaxies that connects everything to everything else. Now bring the view back, slowly, gently, like a camera pulling in from a wide shot to a close-up. The cosmic web recedes. The Virgo supercluster becomes a patch of light. The local group resolves into its main members. The Milky Way fills the view, its spiral arms curling, its bar glowing, its central black hole quiet and dark. We drift in toward the Orion spur, toward a yellow star, toward a blue planet, toward a room where someone is lying in the dark, listening to these words. You. Here, now, safe and warm and held by the same gravity that holds the galaxies. The journey has been long, but it has been calm, and it has brought you back to yourself, carrying the scale of the universe inside you like a soft and luminous secret. There is nothing you need to do with this knowledge. There is no call to action. There is no task to complete, no test to pass, no one to impress. You can simply let it be. You can let the images dissolve, one by one, as you sink deeper into rest. The cosmic web fades, the Virgo supercluster dims, Andromeda recedes into the dark. The Milky Way turns quietly, its arms sweeping through the disk, its stars being born and dying in their slow cycles. The sun shines on the day side of the earth, but you are on the night side now, in the shadow, in the quiet, in the space between the stars. The earth holds you, the bed holds you, the dark holds you, and you can let go. Feel your breathing slow, each breath a little deeper, a little softer. Feel the weight of your body settling into the surface beneath you. Feel the warmth of the blankets, the coolness of the air, the gentle rhythm of your own heart. You are here, you are safe, you are part of something vast and beautiful and calm. The universe has been unfolding for more than 13 billion years, and it will continue unfolding for billions more. You are a single note in a long, slow piece of music, and your note belongs. It has always belonged. It will always belong. There is nothing to prove, nothing to earn, nothing to fear. There is only the dark, and the stars, and the quiet turning of the galaxies, and you, drifting among them, held by gravity, held by the calm. So let the last image be this: a wide, soft field of view, as if you are floating above the plane of the Milky Way, looking down on its spiral arms, and then pulling back and back, until the Milky Way is just one bright speck among many, until the galaxies are scattered across the dark like seeds, like sand, like snowflakes falling in silence. They are countless. They are ancient. They are drifting in the dark, each one a gathering of billions of suns, each one a home to worlds we will never see, each one part of the same long story. And you are part of that story too. You are part of the dark and the light, the gravity and the mystery, the known and the unknown. You are part of the universe, and the universe is part of you. Now close your eyes if you have not already. Let the images go. Let the words go. Let the journey come to its gentle end. There is nothing more to say. There is only the quiet and the dark and the slow drift into sleep. The galaxies turn. The stars shine. The dark holds them all. And you are held too. You have always been held. You will always be held. Good night.